大家记得签到。 喂，你好，请听到声音吗？这边有没有声音，还是他们那边没有声音呢？喂，你好。OK，那现在这样应该是我这边有声音，他们这边没有声音。对，是，有可能他们那边还没架好电。
我的听得到吗？
哎，听得到。
network.
你
It's okay.
It's okay?
Yeah. But I need to connect the Wi-Fi says network. It's okay.
好，可以了，可以。
好。
My phone.
Okay.
线上的听得到吗？
How do you need to take my mic?
No, you don't need. CR is coming. CR is coming. CR 听得到吗？
Hello，可以。
OK.
Good morning.
Morning.
So first, thanks for waiting us and apologies for Danny. He will join us in a little while to help and bring you even more content for today's presentation. So the agenda for today is to deliver a presentation related to mostly transportation installations that are connected to your floating foundation. There are 3 main topics. So first, I give a quick introduction and some context on your floater, on the environment around it. Then there are 3 topics. The first one is about mooring. We will be looking and focusing mostly on mooring replacement, a part of a mooring line replacement. And we can expand the discussion to the broader full mooring line replacements. The second one is a floating-to-floating wind turbine installation methodology, or let's say out of the 3, it's obviously the topic that is the less mature, because it's a topic that is actually having no operational reality yet for floating. And the last part will be about the foundation floater, so that it goes from the loading onto a semi-submersible vessel down to the floater ready for mooring. In between the sessions, I'm happy to answer your questions during the presentation. Please stop me. The idea is, I mean, if I go through 110 slides, I think it's very boring. So maybe if you have some questions, I can expand, Danny can expand also. There will be sometimes focused more on Q&A and extra discussions if we haven't eaten the time in the presentation. And that should round the day. So I count on everybody to participate. English is not my native language. If you need me to slow down, or if there is something you are not sure about what I said, I've put quite a lot of text, so it gives you some time to read also if you want to look at it. But please interrupt me. No problem with that. I am happy to help and to slow down if needed. First introduction is just about me. So my name is Jean-Baptiste Meyer, or JB. That's the short form, much easier for everybody. I'm living in Singapore. I've been living in Singapore for a while now. I'm trained as a structural engineer in France. And I started, like many, in oil and gas many years ago. And I was working mostly on turret mooring systems. I don't know if you see what it is. It's very large internal and external moorings that are used for floating production and storage units in oil and gas. So there are large ship mooring systems. And also doing some construction and construction supervision for this system in Singapore. Then for SBM, still, I worked on the Provence Grand Large, the floating offshore wind that was installed in, the foundations were installed in 2023, offshore Marseille, in the south of France. And I was the TNI package structural lead. So looking exactly after the topics of today, meaning loadouts, liftings, float-off, and all the impacts on the foundation. The foundation was a TLP, but it was designed by SBM. You will see a lot of examples taken from PGL. I'll call it PGL, is the name of the wind farm, because, of course, I have first-hand experience on it, and I have more pictures of it, so it's convenient. But it applies very well to your floater. Then still with SBM, I worked on so PGL is the one on top that's installed. It's just 3 9-megawatt turbines. And then I was engineering project manager for the execution of this one, which is the second generation of TLP from SBM, which is basically, this is the research topic, very reliable and let's say safe. This one is a model that has a lot of evolution that followed feedbacks from the industry, constructability, ability to install, the float-offs. So all these basically have been taken into consideration into the new one. So a lot of these temporary stages, like installation, loadouts, they actually heavily impacted the design change between the first generation, which is installed, and the new one, the new generation of TLP that is being seen. Now, I'm working for Longitude, part of ABL Group. You've had in the past, I don't know for who of you had some presentations already done by Danny or Ricardo in the past. They were already with Longitude, now for WC. But basically, Longitude, we cover one of our main business line is offshore wind design and engineering. We have foundation design also, not floating, but fixed. And then we are also looking after ship design engineering, facility and subsea oil and gas, and marine operations is transportation, installation type of topics. And just to connect to Danny, Ricardo, and the people you already met, so we are all part of the same group. ABL is the marine warranty surveyor, are basically the experts and doing surveys, doing inspections. AGI is not relevant for us. It's about well services, so it's a downstream, upstream activity, sorry, for oil and gas. OWC, there are consultants purely in renewables, and Longitude, we are doing only engineering, but across business lines, not only for renewables. So that's for me. Then, to give a bit of context, I mean, I'm sure you're very familiar with your own floater and the sites. So we have been working around in these method statements or the reports that were issued in this presentation around the Delta floater that you have developed. It's a semi-sub, so compared to the TLP we saw just before, it is not a turbine center, but a turbine mounted on one of the main columns. And the dimensions are today for turbine around 15 megawatts for the NRL, with let's say a large footprint for a semi-sub. So quite a, I would say, a standard semi-sub structure. Today, when I looked, and the first point I want to make on this intro is about the criticality towards weight. So I know we're seeing the introduction part, but just taking the opportunity here. Basically, we have been provided, and you have been working on weights, and obviously the primary contributors will be your turbine, will be your primary steel. But you will see that all these operations are extremely critical to weight and to the contingencies that you're taking. So a proper construction of weight budgets, weight contingencies, understanding of not to exceed weights are basically critical even at very early stage of design. So I don't know if for a given turbine, have you defined already a not to exceed weight, for example, for your turbine, for your foundation?
Not yet.
Okay. So you will see something that needs to come very early in the development because the impact at all stage of operation, not only the in place, are quite severe. And that's really just to highlight what I want to bring today. Danny and Ricardo, I know I saw the presentation they gave. They gave a lot of very technical and calculation, and but you are way better in calculations than I am. I am better at running an operation and giving you ideas on what it needs to actually happen in terms of preparation, in terms of execution. So that's what I want to bring today. And just to complete the view on the point of weight is that's what I was saying, that it has to be developed, and basically that's the ISO definition of the weight. Your not to exceed is the up line here. This one needs to be defined extremely early in your project. And after there is the understanding of the difference between net weights, gross weights. Where do you have your own contingencies? Where do you have some subcontractor contingencies that have to come, for example, for specific operations? Sorry. Correct.
Show me. Okay.
Yeah. So just to talk on the weight part. Mooring side, it's a very standard catenary mooring line arrangement with nine lines, all full chain. You have some clamp weights. You have some clamp weights also. It's quite a big chain, I have to say, 152. But it is in the market, so it can be used. And for now, on a generic, let's say, case, you're using drag anchors as a base case, which are indeed very practical. The turbines that are associated to your foundation, so we said that it was the 15 megawatt NRL. Now you're working towards commercial models, because commercial models data have become available. And so you're working with a Siemens Gamesa 14 megawatt, 236 meters, which is one that is starting to be widely distributed offshore on bottom fixed. And it's a significant change compared to the one that you're running now. If we compare the two, I mean, the power obviously is obviously roughly the same. The main change that we have, and which shows a bit of misalignment, is on the tower. Today, the tower assumptions that you have taken, show directly, but basically would not work on your floater. You're missing a part, basically. You're missing a part at the bottom of the tower. So either you have a transition piece. It doesn't have to be a transition piece at the sense of bottom fixed, but basically an interface, or you need to extend your columns. So when we looked at your weights, and obviously there is a large weight difference, but a lot of this weight difference is created by your hub height. You have 30-meter difference. You might not need 30 meters to create an air gap because you have a slightly smaller rotor. So, but this basically part here, the bottom of the tower interface will need to change, and that will impact your weight budget, and that also impacts obviously your accessibility. How do you access this interface if this interface is already high above deck? You will need access. You will need all this. So it's a critical point to take into consideration. And obviously, anything that you have developed related to the weight of the foundation. So as we said, we saw just before, where you will need to include a gross weight approach with contingencies and so on, plus the impact of the turbine. It will impact, for example, your ballast system. It will impact the operation case that you have planned will be impacted by this change. Now, looking at the installation sites that that you have taken as a base plan, it's west of Honshu in northwest Taiwan. It is a fairly shallow site for floating offshore wind. Today, 60 meters is an area where you can start to compete with bottom fixed. I mean, it's more like bottom fixed is starting to encroach more and more on the lower limit of floating wind. And the performance of floating wind in 60-meter water depth, especially when you have a high draft like your semi-sub, it is really, I think, probably a lower boundary case that you have. But that's a fairly good site. It is a site that is impacted by seasonal activities. I mean, like all the weather in Taiwan. I'm not looking in terms of resource for your turbine. I'm just thinking when I see the graph here, which is the Honshu Boy statistics. Basically, you have 3 months, like December, January, and February, or November, December, January, that are beyond 1.5 meter HS. And it represents more than 30% of the time. So you will see we'll talk a lot about window of operation and how long do we need to plan an operation. The operation maybe can take half a day to do. A lift is fairly short, but all the steps that you have to conduct before that are weather restricted until you get into a safe condition. They will define your weather window, and having high statistics, for example, in a month of returns above beyond 1.5 meter will have a significant impact on your ability to do the installation operations, the float-off operations that are weather limited. But overall, you still have very nice seasons, especially, I mean, like most of the northern hemisphere countries, but around the summer, I mean, late spring, summer, early autumn, you still have a very good season where you probably have weeks of forecast with very low wave and wind conditions, which are beneficial for all this installation stage. So you're not really in a logic if we project your floater in a more industrial type of production, so where you're not only building 1 or 3, but you're trying to build 20 or 50 of them, you will be in a methodology where you will have to focus your installation on the season and keep on building and storing off season. So it's complex execution strategies where you will need to manage basically your supply chain down to your pre-assembly, assembly, installation offshore in a stream, because you can't store 20 turbines and 20 foundations so easily. And last, the marshalling site. So the marshalling site is basically the locations where your components could start from. Looking at the ports on the western coast, the obvious ones and the closest ones are Taipei Port and Taichung. They are both roughly at the same distance of the site, around 40 nautical miles, which is extremely good in terms of site selection for you. It's barely half a day of tow at 4 knots. So which means that basically you can leave in the morning and be in a station keeping mode in the evening. That's good, provides lots of flexibility. And that's probably too optimistic. As I said, the day you will go into understanding higher production quantities, this very short supply time of your foundations, of your mooring lines, of your anchors to the site might not be applicable for the rest of the sites. If you have a site that starts to be further offshore, that starts to be further from a port, then the impact of transit time for your floaters, for your turbine components, your mooring components will start to have a heavy impact on your execution. But today, that's the case you're working with, and it's quite favorable for you. That's to wrap up roughly an introduction and just putting back some context. I assume that you're all working on the foundation design, or is it a broad team that are not necessarily connected to the work on the foundation design?
Not all of them.
Okay.
Somebody will focus on whether with metal. Yeah. So somebody will focus on maybe cable system and installation, lifting. Yeah. So.
Very good. So now let's start with one of the 3 main topics, unless there are already some questions or some things on the intro part or no? No. Feel free to stop me. Really, else I'll get very tired. So the first topic we want to look at is the mooring repair. So all the 3 parts, the 3 main parts are structured the same way. First, we'll be looking at a very high-level view on who are the stakeholders for this operation, the main stakeholders. We are not involving everybody. What is a broad timeline for this type of operation, from basically the very early operation preparation? And you will see there is a big focus on the operation preparation more than the actual execution, because if everything is well prepared, the execution is it's a PowerPoint of drawings. It's very straightforward. And then the selection of assets, selection of sites. Then I'll go on the operation preparation. So taking a few of the main stakeholders and looking at what are their main contribution to the preparation. It can be physical preparation, can be engineering. So there are a range of activities that are needed ahead of the operations, and then the operation execution itself, which then goes through the sequence drawings and the steps that are necessary for the operation. So first thing, the moving replacement is actually the most straightforward of the three topics because the number of interfaces is very limited. You have only two main stakeholders. You will have the delta float designer, yourself or a company that carries the design of the floater, and you will have a moving installation contractor that will be selected for the operation. I don't think SOIC operates any assets or intends to do the operation themselves. So usually that's the setup that you will have. When we look at the key milestones and how it's being prepared, again, the mooring replacement is the most straightforward one. It's the one that requires the less or the least planning. We are only talking about a few months that would be required to basically prepare and execute the operation. Reason being that a lot of the work for the mooring would have been done by you already for the installation stage, the hookup stage of the foundation. So a lot of the analysis, a lot of the work that can be time-consuming, basically, you already have it. And the conditions, they will not change for the offshore operation. So in terms of engineering, then it's only about adapting the procedure to the actual issue that you have. So if it's a partial replacement, if it's a complete replacement of one mooring line, or if it's the replacement of the full mooring system, then obviously the steps are different. You will have to run different type of analysis, but you have the models existing, you know the environment, and you will only have to adapt to the assets that the mooring station contractor will bring. So a few months before, what you want to do is to start operation engineering. So it's not so much the engineering of your asset itself, it's done already. It's really about operation. It's about understanding what kind of asset you will need to select and go to contract and discuss with a mooring installation contractor that will propose a vessel, an AHT, that will propose an ROE spread when you need an ROE, and start basically this loop of defining the operation. You can be also in a mode where it is an emergency repair and you need to mobilize quickly. In this event, usually you would have prepared with the development of your farm or the development of your foundation, you would have prepared already your repair plans, which means you would have spares already allocated or stored somewhere, not only for the chain, but also for all the accessories that go around the chain that are required when you do, for example, a partial replacement. You see there are some accessories that you need to do that. So it can be a philosophy where in your onshore base, your maintenance base, you maintain some components. So you can have purchased extra chains, for example, extra accessories, so that you are in a state of readiness where the procedures have already been prepared and they just need to be adapted to the asset you will select. So this will start, it can start within a few months before the actual date. We cannot do it in a week time. We are seeing extra fast mobilizations, for example, for so you were mentioning cables. So we are doing that also. Cables, we can do mobilization within a couple of weeks for a cable repair, but it is standardized. There are less risks, you're only handling the cable. So yeah, that's the magnitude is more towards a few months for the chain replacement. Then in the weeks before, you would have to complete your operation engineering. I'm sorry, it's a bit small for you. And with this operation engineering complete, you can mobilize your AHT. So you will have your contract would have been in place a few months before, and you need to bring the AHT to your marshalling location. You will have to bring your AHT and basically prepare the AHT together with your equipment, together with your chains and anything that you have to supply or taken from store to prepare for the operation. So the AHT preparation is more or less limited to the deck and the chain lockers, and you will see after, and I'll show you more in detail. Then, in the days before, what you need to do is that you need to secure everything to the deck. You need to make sure that everything is ready for sail away, because you will have to wait, and we'll see later in the presentation. It's not because you decide to have the operation on a certain day that it will happen. All these operations, they will have weather restrictions, and especially for moving, when you might not have the luxury to decide when it's going to break. If you need to trigger a repair, you might have basically to stand by your AHT with the equipment, with everything at readiness, to wait for a safe window operation. So it's a different approach from the other two topics, meaning the turbine floating-to-floating installation and the loading float-off, because here you're not in control of when you will need to do this operation when it's an emergency repair. If it's a planned repair, then fine, you choose the best season and you can leave faster. Another thing is that sometimes, and I haven't seen any secondary steel design on your foundation, the installation aids that you would have used to hook up your foundation, so basically to pull your chain, sometimes they are on the floater itself. But because you don't want to buy as many winches as you have chain connectors, as many sheaves, as many, so sometimes you will have purchased a few of them, and you would use them. Let's say you take you have two full sets for two floaters, and when the first floater is finished, you transfer it on number 3. When the second is finished, you transfer number 4. And that means that by the end of the operations, all your floaters, they don't have any of these installation aids on board anymore. So unless you have a method that relies on external crane, for example, to pull your chain, do the tensioning, you might still need some sheaves that have been removed. And basically, all this needs to be reinstated before you start your operation. So it's a side activity that can be prepared as you are in these months, weeks before. You can bring your installation head, you can install them, you can test them offshore, and be ready in the same time as the asset is ready in the harbor. So this sequence is the same, and you will see it for the 3 parts because it's a critical aspect of the planning, is that while you will define and you will know your regulation rules once, you will have an overall planning. When I say overall planning, it's not to the day or to the hour, it's basically the general sequence of your events and an order of magnitude of the planning. So who needs what and when to execute. Once your design brief and design basis have been established, these 3 components here, they won't have to be revised. Basically, they won't impact the time needed to deliver your engineering and your operational procedures. Where you can not lose time, but where you might need time is the iterations that you have to do between your engineering and design verification and the connection to the operation procedure. So, and that's really the critical point, I think, is that today you are very focused on the engineering design verifications in place condition. But the day you will discuss and you will have to place contracts with other contractors that have their own limitations, then they will feed back some data that will impact your engineering. And that's where I want to come back to the example I was giving you with the PGL, the SBM plotters, the TLP. You will see, I mean, here the first generation was fully in the water, you couldn't see, but it's a big, small bracing, big truss structure with permanent buoyancy at the end of the triangles. There are some pictures later. Versus the second generation, which is like a tubular, very simple tubular structure with a main column and three arms. One of the main reasons in the design change is not because SBM wanted to make a different design just for the sake of it, is the impact of all the temporary transportation conditions, installations, the ease of assembly before loadout that has impacted. And so SBM, they downgraded their engineering expectation, where the PGL project that is installed in the water today is probably the most performant TLP with the thinner tubes, I mean, the smaller diameter tubes, the least drag impact. Basically, the effect of the waves and current on the foundation has been optimized. But it was developed at a stage where SBM was looping engineering design verification between R&D departments and disciplines. And that's a very, it's very good engineering work. But once they faced operational procedures, once they faced operational people, then you see the difference it made in the design in the end. So it is normal to see this kind of impact. And here today we are talking about just a few of the topics of installation, but you probably have had the same feedbacks and discussions on other related topics. Your initial hookup, obviously, is one of the main ones. Or, for example, quayside integration of the turbine would have been the same. You would have been interfacing with the OEM and a lifting contractor. So that's a main point. And this process here is what will consume a lot of your time. And that's what can derail your project. So the early engagement of operational people and companies that deliver operational services is critical when looking at design. Sometimes it has to be done through consultancy. Sometimes it has to be done because there is an actual foundation that's going to be built. But the first loops of this are going to be very time-consuming. So in the selection of the stakeholders, one of the critical points, so we'll have the same for the three parts, is always going to be the selection of your assets. Because that's what is going to make the biggest difference in your ability to execute. For the mooring system, it is less true because you have less direct interface between the asset and your foundation. But for the other two, you will see it can have significant impact. So the asset that we need is very similar, if not, it can be even a bit smaller, than the assets, the HT, that you would have required for the hookup preparation. So I don't know what's your current sequence, but usually you would prelay your mooring system in place. So you have 9 lines to prelay per foundation. So to do this operation, you will bring a large AHT. When we say large, it can be AHTs that have beyond 250, 300, up to 380 bollard pull, for example. The reason being that in your case, you're working with drag anchors, and that the drag anchors, their only downside, I would say, is that they have to be field installed and they have to be load tested. You have methodologies to use pulley systems, to use smaller bollard pull, but ultimately, when you have to play, so install or remove reinstall anchors, usually your AHT will be bigger you will need a bigger asset. In the case of just replacing a section of a mooring line, you can manage to have a much smaller asset because the station keeping of your foundation will be done by the remaining 8 mooring lines. And the only load that you need to transfer is actually the chain weight and the chain loads coming from the environment when you're bringing the chain on board. So that's why you will still need to look at the bollard pull capacity. But in this case, this one's 250 ton bollard pull. That would be more than sufficient, for example, to do the operation. One of the critical items on top of the bollard pull is going to be your deck space. Depending on the length of chain you intend to replace, so you have 560, a bit more length of mooring line, short mooring line. It is going to be one of the critical points. You have some AHTs that are usually with very high bollard pulls, very high winch rating, but they might have a smaller deck because, for example, they're focused towards anchor installation, and they are very, let's say, powerful but smaller type of vessel. So in your case, you need to have sufficient space to bring the chain up to the damaged section on board. You need to have space to walk around, and you need to be able to bring the new chain once the old chain has been basically cut and secured. You need to be able to bring in the new chain. So the new chain, you can store it in the chain locker, but one day you need to bring it on the deck. And it depends how many meters you're replacing. If you're replacing 20 meters, is nothing. If you start to replace more than 100 meters, you will basically start to have to lay up the chain up and down on the deck, and that takes a lot of space. Mooring winch capacity is obviously, it comes together with the bollard pull. There's no direct relation between the two, but it is basically your ability to pull the chain with the vessel. ROV spread launching, it is quite rare to have ROVs directly on HTs, or they are very small. So usually what is being done is that when you need ROV, either you bring a separate asset, but it's very expensive, or you put a temporary ROV spread and you bring some ROV specialist on board, and they can operate like this directly from the HT. Then availability on the market and day rate, it comes together. It is not very critical for an AHT. We'll see later. You have in the region a market that is quite developed with regards to AHTs. You have a lot of TNI projects in the region. So you have a lot of anchor handlers, ocean-going AHTs that have sufficient capacity to work in the region. And yeah, so as I was saying, it's actually a case where you will probably need an asset that is smaller than the one you would have used for your initial hookup. So when looking at the AHT and what are the main components I was mentioning, and that are the ones we want to look at. So as I said, the work deck is basically what you need to use to do your layouts. When you will start to do your operation step by step, you will need to verify that you have sufficient space on the deck to lay your anchors and work safely around it. Another critical equipment is your ability to lock the chains. So in this case, there is, in this example, there is only one. So that's the stern roller. So it's big rolling tubes that are at the stern of the vessel. They use basically they are helping when you're having a chain that is being pulled or let down from the deck. It helps basically holding the chain in and out. And in front of them, you have what's called shark jaws. So I don't know, I haven't put a picture, but it's two wedge structures that will rise. And when they rise and you have your chain engaged, because of the cross pattern of a chain, the chain will be locked basically here in the shark jaw. When you do work on the top chain, you retrieve all the top chain until basically below the elevation of the distance of your repair segment. So you will only lock one end of the chain. You have cases, and that's, for example, what happens for cables. If you have to replace, for example, a mid chain or a bottom chain, you will not necessarily want to retrieve 100% of your length on board. So then you will have to secure basically two ends of the chain, but that needs to be permissible by your chain length with respect to the water depth. So it's something that sometimes will trigger having to cut subsea to retrieve only one end, because you cannot do the full retrieval without cutting subsea. Next critical component, we said before, anchor handling or winch for towing. In this case, it's being used for the handling of the chain and all the anchors. Another point that often is forgotten is that all the operations you will need to do, you won't have only the people of the vessel on site. And because you want to keep your costs low, you need to house, basically, you're not going to bring another asset. And it's not like oil and gas where you have accommodations on your substructure. Here, nobody will be on the foundation. So you need enough accommodation to have your crew of the HT and also the people who will work on the floater itself, your clients, your supervisors, and all that. So you need sufficient people housed in this HT to run the operations. Now the HT, they tend to come with quite large accommodations, but we have seen limitations where we had to bring another asset, usually another AHT that is only being used to have people on board. Sometimes when you have the choice, you can take one where there are multiple. The other critical aspect is it's summed up down to the bollard pool, because in this case, the station keeping ability of the AHT is less, I mean, the maneuvering ability is less critical, but it is still important. When you will have the chain that has been picked up, you'll see later, you cannot afford to have the chain that starts to go around, hits the chain beside, or even worse, if you have cables that are subsea. So you need to be able to operate with a good level of accuracy on your positioning. And that means that the vessels and the DP rating of the vessel will be a factor when you will want to choose on top of the bollard pool. And that makes the difference usually between what we call like harbor tugs, for example, or let's say you could have tugs operating near shore that have very high bollard pool, but this bollard pool is usually destined to do towing operations, so pushing or pulling a vessel, and they don't need an as good position control. They just need a lot of power. So here, this type of maneuvering ability usually comes from the offshore AHTs that you will find you're using them around wind farms or oil and gas platforms. And last, it's shown on the picture, but actually is not required. It's a nice to have when you have it, but you don't necessarily need a crane. And that's a bit of a misconception. When handling mooring lines, usually they would rather use auxiliary winches. So they will weld or bolt smaller winch on the deck to handle the chains and bring the chain on the deck rather than a crane. The crane, I mean, first you will never use it to pick up the chain from the sea, but even just to handle the chain on the deck, it's usually not as efficient to have a deck crane rather than having properly positioned deck winch. So that's why you will usually operate one main winch, and then you will operate, if it's a simple operation, two smaller auxiliary winch on the deck to guide the chain. So basically, you will try to guide the chain. For example, if you want to bring your component to be replaced on the side of the deck, like you will use the one auxiliary winch from the side, and you will release from the other one. And basically, they can do everything with that. So deck crane, not necessarily required. If it comes with it, nice to have. So that's for the critical steps in terms of the few stakeholders. As we said, for this one, there are not many. And the assets, the main assets that you will need for the operation. So as we said, we saw for the mooring is very limited. It's quite straightforward, the operation. Now, looking at operation steps. So the operation steps, the first one that we want to look at is the mooring station contractor. So as we said in the stakeholders, there are only two, the Delta Float foundation designer and the mooring station contractor. So looking at the mooring station contractor first, usually they are the ones who will do the coordination of the work. They will be the one setting the systems in place, and the foundation designer will support them. After, it's not a matter of contracts or anything, it's just a matter of who takes the lead and the ownership of the risks and the ownership of the procedures. So in this case, it's going to be the mooring station contractor. The mooring station contractor can either have their own asset, so they operate a fleet of AHTs, they are available, they are suitable for the operation, fine, they use it. But more often than not, it's not the good AHT that they have, or it's too expensive because it's too big and not necessary for the operation, or just not available. Then they can charter another vessel, so they rent the vessel, and they can bring their own crew. It's not going to be 100% of the crew. You will always have, the vessel owner will retain some of the core functions that are related to navigation. So the captain, the first engineer, all this crew will remain with the vessel usually. It's not a bare, it's what we call, the opposite is what we call a bareboat charter, which is you rent just the hull. I mean, the vessel with nobody on it. In this case, for this kind of assets, it doesn't really happen. You will always have the marine crew that stays with the asset. And so the marine station contractor will bring people who are specialists for the operation. So they'll bring riggers and safety people and whatever. And the main responsibility of the mooring station contractor through the operation preparation is going to be first the specification and to give the understanding of the team needed for the execution. So it's going to be a combination of their own people, the people from the vessel, and the foundation designer. Usually, the foundation designer, they will send some. They can send some people offshore, even if it's just as a representative. It can also be. You can also have some clients to manage. You can have a marine warranty surveyor to manage. So all these teams and who is responsible for what, who reports to who, and who takes the final decision or the final sign-off. That's the first thing to agree and to define when you prepare this kind of operation. And you will find for all the three sections, you will find roughly the same architecture every time. You need to know who is in charge. Sometimes it's more blurry. We'll see with the photo, it's a bit more complicated. Then the first priority is going to define the methodology and the assets that are required for the changeout. So the asset is not only the AHT. The AHT is the first piece to the puzzle. But you will also need a lot of tools and installation heads and services around the operation to make it work. So here we took the example, one obvious one is if you want subsea monitoring and some subsea connections, you will need an ROV basically to come, do your subsea connections. You're not going to send divers now. It's not really done so much anymore. But you need also to define your lines. So a fishing line is a line that you're going to use to basically hook your chain. Your messenger line is what you're going to use to pull your chain. So you need to define them, size them. Then you need to define and find what system of buoy do you want to use, because you will try basically to release some of the tension in the chain by using some buoyancy. you will also need some temporary or permanent edge links. So the permanent ones, they are the ones that are going to connect your new chain to the old chain. Temporary ones, they can be one that, for example, used to pull your chain, used to secure your chain on the deck. You can use these links at many locations. And they are not the only one. You can use chain shackles, for example. Then, as we said before, they will need to check that and to do the proper layout of the operation to check that the HT that's selected has sufficient deck space, to work on the chain to be cut, and also to bring the new chain. And if you don't have enough space, which can happen, then, or for example, if your operation is much bigger, you replace a lot of lengths, you replace the anchors, then you will never manage, obviously, to have everything on the HT. After, it's a matter of operation planning. In your marshalling site configuration, it's a very favorable configuration. It would make sense to only use your AHT. And basically, when your AHT does one operation, comes back to the marshalling location, you load the rest of the chains or anchors that you need, go back offshore. You're losing 1 day. It's not much, but if you start to get further than that, and you start to need to have some logistic time when you take your AHT out of site, you want to maximize the time of the AHT on site. So you will take a flat top barge, you have like 300-foot barge that are being used for that, with a small tug. And the idea is to feed your AHT with the components that they are missing. So like this, they don't store too much on the AHT, and you will bring in the new components, take out the ones that you have replaced. So the feeder will work in both directions to make sure that your AHT will focus only on one thing, which is replacing the chain again and again. And like this, there are no routine where when you need to do change out of maybe a few lines, but for many foundations, we are talking about weeks of operation, and you can lose days after days just in logistics when it's not properly planned. So develop the top chain or any chain part change out procedure. That starts to be a bit more in the practical way. Execution schedule and operational envelope, they come together. You will need to gain an understanding on how your operation will be affected by weather. And it's not just the operation, the AHT, it's the operation. What is going to be the response of your floater when you will remove a chain? And basically, you need to stay in a safe condition. So it's a planned operation. It's not like a one-line broken case that happens without notice, but it comes close to it. Usually, you would have done verification for a one-line broken case, so you're confident that your floater will stay stable, even in an environment that's fairly severe. And that's why change out of chain is done one by one, because it has been, as we said earlier, it has been covered already by your analysis. We know the floater will pass. But now, when you need to plan and do it, you obviously need to understand when can I start the operation, and do I have enough visibility on my weather to do it? And we'll see a bit more on that. And so the execution schedule, usually on this kind of operation, it comes down to a level of details of the hour. So it is a very accurate planning that has to be done. It will be developed based on your winch speed capacity, on the retrieval length that you need to do, on the number of links that you need to cut. All this, the mooring station contractor knows how to quantify. They will give hour by hour schedule for all these activities. Again, the reason is if you do an approach that is not as narrow as that in terms of schedule, and you have to do this for 20 foundations, for example, on a farm, the amount of time you lose at the end, or what you're going to miss in terms of planning at the end, is by days. And we all know day rates, even on an AHT like this, it is a significant cost, and we all want to minimize the cost of it. then just because they are the ones leading the operation, they will need to develop management of change procedure, task plans, and hazard identification, and hazard is hazard operation. So it's basically the framework under which everybody is going to work. Hazard is mostly about safety. Task plan is about the actual execution of the task, and the management of change is when something is not going to plan, how do we react? What is the chain of command? What do we stop? And basically preparing for all the case of change, or at least having a framework for it. So these are more general documentations that they need to prepare, but they are necessary to execute the operation. So the first practical thing, that will have to be prepared is actually something that is going to be done in conjunction between the mooring station contractor and the foundation designer, and it's a mooring analysis. So it's not the mooring analysis in the way of the installation and the hookup. It's about understanding the relationship between your AHT selection, the available bollard pull and winch capacity, to the loads that are going to be imposed by your chain. So it will depend, obviously, on how much of the chain do you want to retrieve, how much, and do you need to retrieve your anchor or not, and all this, basically the dynamics of the mooring chain being transferred from the floater to the AHT needs to be understood. So it's pretty straightforward analysis compared to even the hookup. It's basically the reverse of the hookup and the chain handling. But it is a study that has to be done. Usually, it's going to be the loads output are of the interest of the mooring station contractor, but the methodology and the analysis is usually done by the foundation designer because they already have the mooring models and the chain model. Another type of analysis that they need to conduct is dynamic positioning analysis. So it's going to be about the ability of your vessel to stay in position. The AHT will still work in close proximity. We'll see later, but as much as you want to try to gain some space between the foundation and the AHT, you're not going to go very far away. You will still remain within 100 or 150 meters from the foundation. And that means that the ability of your vessel, once you've started repairing your chain, your asset is physically linked to the chain. You're not going to just dump it over the water. You need to finish your operation. So we talked about the window of operation, but here it's also about the ability of the vessel to maintain against current, against wind and wave. That's the whole concept and the whole charting that you see here, that's a DP plot, DP capacity plot. It's so if we take, for example, that's your vessel, that's the fore, that's the aft. So the green curve around and the green and blue curve. They are both just two different methodologies, but giving similar results. It just shows that if you take wind and wave combination, basically weather combinations in your propulsion system direction, obviously that's where you have the most control. So it's fairly easy to position your vessel, and that should imply that when you plan your operation, the heading that you give to your vessel when you're doing your chain repair has to be to face let's say the most frequent and significant weather events that you get in your window of operation. That's where you should try to maintain your position. That's where you will have the more power. And you can see that as much as you have thrusters to control side motion on a DP vessel, it is much more limited. You probably have only a third of the capacity to hold the weather in transverse direction, in beam C direction, compared to the fourth one. And it is not symmetrical fore and aft for the reason of the position of the thrusters. So in this case, you can see that this one has some stern thrusters that are probably with an azimuth control, so you can turn them. And you have some bow thrusters, but the bow thrusters are always less powerful than your azimuth thrusters. So that's why you're not as wide. So that needs to be well understood, and that will define the position of your AHT, the clearance that you will need to maintain with your foundation. So if they have a weather forecast where they will never exceed the operation mode of the DP, you can take a smaller distance and basically retrieve less chain also on board to do your repair. Now, usually, it's never going to be, and an MWS especially will not just look at your intact propulsion system. They will look at your root cause of failures between your thruster systems, your propulsion systems. So they will try to look at the case, okay, I lose a power gen, I lose a thruster, I lose a burst somewhere. How does it impact my ability to control the vessel? Do I lose fully the control or not? And the redundancy of these systems is what we call the rating of your DP system. So you will have a DP, now it's mostly DP2 and DP3. A DP3 system, for example, will have a fully redundant system that allows you, even if you lose, for example, some part of your power, you will still remain in control with 100% of your ability to control your position. The type of rating of your vessel also makes the price and the day rate of the vessel. So you need to specify. You don't need to over-specify. If you know that you can take a large contingency in terms of distance for your chain repair, you should do it basically, rather than paying something that needs to be in very high level of DP. The next preparation for the mooring station contractor is about the ROV. So as we said, usually the ROV is not going to be found on a standard AHT spread. You will need to bring it as a module, and it really comes as a package. That's a package. That's an ROV spread. It comes with so the LARS is this launching system. It comes with the tether management, and so basically all this is containerized. They bring their own people, they bring their pilots, they bring their supervisor, and they work from either like they have their own small control room in the container, but basically they can do independent operation. It does take some space on the deck. So again, we are back to the topic of controlling the deck space and making sure that we have sufficient space for launching and but it's fairly standard. And you have a lot of suppliers that can provide this kind of launching system. Now, so that was for the mooring contractor and the main items to look at during preparation. Now, on the foundation side, it is because it's not. I mean, you might have planned for it, but the first thing to look at is going to be, so I put it on the picture, you're going to look at your ballast system. You will run all the calculations before, but when you're doing your hookup, in the case of offshore wind turbine installation, it means that when you've done your hookup, there was no turbine on the floater. So your ballast management of the floater is not applicable to this case or to the repair case. Because in the repair case, you have your turbine that was operational or that is put in safe mode or in braking mode. And so you will need to develop, if not prepared before, a new procedure and new management of your ballast to ensure that when you're disconnecting the line that you need to repair, you're not going to create over tension or over excursion of your asset. So usually you will need to either I don't know if your floater your ballast is set for once for all operation stage, or do you have active management? Do you have active management of the ballast during operation, or?
我们是 active 的吗？不是 no, I mean not active.
Only once, huh?
Yeah.
So and that's good. that's better for operation. But it means that when you need to get into this kind of a repair sequence or a new operation, you need to come back, reinstate your pumping systems, test them, and adjust basically, and have people being able to adjust the ballast when you're removing the line. Why it's let's say the good option to look at the ballast system. It's when you're doing the hookup. Usually, the way you would do it is you will do the hookup with a deeper draft on your foundation. You will deballast with all your lines connected, and before you do the turbine integration, and then you will do a final adjustment of your ballast. As you're doing the turbine integration, you adjust your ballast until the final operation condition. But in this case, it means that your pretension in all the mooring lines are locked by your floater buoyancy. So you have created, so when you do a pull with your lines, you are not going to put a very, very big winch or a very large offshore crane to pull the pretension levels of your chains. I haven't seen your hookup procedures, but usually that's what we will try to do. So you pull sufficient chain to have a position control of your foundation, and the pretensioning of your mooring system. You're doing it by doing a final deballasting of your foundation to create tension in your mooring line. So, because it's a very cheap way of creating pretension in a semi-sub foundation. So, like this, the pulling system that you have during the hookup can stay fairly small. You don't need a very big winch on your foundation, or you don't need a very big offshore crane to pull your chains. But it does create the opposite problem that when you need to disconnect your top chain, you have this pretension that's locked in your chain connectors or in depending on your connection system. So you will need to play with the ballast to try to release some of this pretension at a level where you can do a pickup, disconnect your locking system, retrieve your line. So that's why a lot of the work in the preparation of the floater is actually going to be in understanding the procedures around the ballast and how you're going to manage the tension in your line so that you don't have to bring a very big crane offshore. So, yeah. Basically, the last point was about the fact that we are going opposite the hookup tensioning sequence. Now, the next critical point to prepare on the designer side is in the understanding of the weather condition and the operation envelope that you want to define for the mooring replacement. Your floater, when you disconnect a mooring line, will behave differently. And you will have, because you will have to play on your ballast to try to relieve some tension in the line you want to retrieve, your excursion envelope will change and your motion envelope will change. And that's why you need to do it in an environment that is controlled and let's say enough weather visibility to do it. You are not going to do it in the cool months of December. It's not only your floater, it's also that at this stage, you're also fully connected with your electrical cables. And when you would have done your initial hookup, it's not the case. When you're doing your initial hookup and you go through your ballast sequence, you can afford to have large excursions as long as your mooring system can take it. But typically, when you do a hookup with a combination of tugs doing station keeping and bringing in the mooring lines, so on each of the three sides, and then doubling them, tripling them, and tensioning, you will have some envelopes of excursions that are quite large, and it's fine because you're not creating much tension in the mooring line, and your safety system are the tugs doing the station control of the foundation. Here, you don't want to bring station control with tugs on your foundation, but you need to stay within an excursion limit that is compatible with your electrical cable. And that's the main point, is that your mooring system will not have a problem, and your one-line broken case, in extreme case, in operation, you have proven that your mooring system can take it. But usually you will accept, in these events of one line broken, for example, in a storm event, you will accept some higher bending limits for the cable or excursion for the flopper. Here, if you're doing this operation and your intention is to replace a part of the chain on every line of the foundation, you cannot create this event 9 times without risking damaging or breaking the cable. So again, a very good understanding of what limits do you want to set yourself for the weather in terms of wind, wave, current, to limit the risks on your cable is one of the critical points to have in mind. So that means that you will need, if you define by your engineering work, you define a weather window. You say, okay, I don't want an HS that will exceed this value from the moment we start ballasting to the moment we are fully reconnected. It means that you will need to do weather monitoring. It means that you need to understand how weather monitoring and operation readiness and start of operation is triggered by weather monitoring. I mean, you will see if you take the DNV ST N001 guidance with respect to weather restricted weather operations, you will see what it imposes on the operation. It is a lot of methodology. And that's why it is summarized, and that's the DNV extract. And summarized here is your ability to plan and to start a weather restricted operation will be conditional only on your ability to have weather warning and weather warning that covers a sufficient duration to cover not only your estimated time for operation, but also DNV, for example, will impose you a contingency period, and that will drive basically your total weather window, except that your required weather window, as we can see here, starts at operation starts, but is actually to be extended to the previous weather forecast. So if you have weather forecasts that are issued daily, for example, it means that it assumes that your operation starts, you will basically start at the weather forecast. And you will need to cover with the regular weather forecast and show that you have enough visibility on your weather forecast until the completion of your operation. And so the total required, the total operation reference period is actually always greater than your required weather window. And that can impact significantly. If you don't have daily reports, for example, for weather monitoring, it can become problematic because you will basically have an operation reference period that will increase. And I don't have the table here, it's later in the presentation. I don't know if you're familiar with DNV ST N01, but if you are, for example, below 3 days of operation reference, the weather limits that you can apply are fairly benign. It's less than a year return period. It can even accept seasonal full forecasted value, meaning only based on the forecast of the weather provider. If you have an operation reference period that is between 3 and 7 days, you can still go for some seasonal aspects, but you need to take yearly for the wind and 10 years for the waves return period. That starts to be significant. Even if you do, again, you will always try to do seasonal approach. DNV allows it for you. In a case of Taiwan, you don't want to do yearly return periods because of your winters. You will not, if you have the capacity to plan this operation not as an emergency, but in a good season, obviously it's going to be a lot more favorable. Else it means taking 10 years return period on events that are extreme events. You have typhoons, you have winters, and basically they will tell you if your operation reference period is greater than 3 days, that's what you need. And in 3 days, I mean, that's why I come back to the timeline. In 3 days, you need to have your ballast operation. Basically, it's the operation start. So you need to have your ballast operation done. You need to retrieve your mooring line, repair and replace your mooring line, and be back in a safe condition with the mooring line, basically pre-tension again on your foundation. 3 days is nothing. It's not enough, clearly, to do this operation. You will more likely be in a 3 to 7 days type of operation when you do a mooring chain replacement, at least for the first ones. Maybe after you will find ways to manage, prepare the ballast before without basically compromising the floater condition. You can try to save a bit of time, but that's the range of time that we are looking at. And obviously, you have operation reference periods that can be greater than 10 days, or even more. Like, for example, when you have mooring at a quayside, we will see later, but when you have to bring a cargo on semi-submersible vessel, you need the time to bring the cargo on, secure your sea fastening, weld, do your NDTs. You have a lot of operations that happen, and you can have to wait because once your vessel and cargo are ready at quayside, it doesn't mean they are leaving. It just means that they are waiting for the window to open offshore. So if you don't have a contingency period to say, okay, I'm going to wait in a safe area, your quayside mooring system for a semi-sub vessel will have to be designed for events that are usually all around 10-year return period. And it is fairly severe because it means, we'll see later, but it will impact the quayside equipment that you have, your mooring lines, the equipment that you have on the vessel or the barge for your connection. So it is critical. And that's just a view of what a weather warning alert system looks like. So these ones, they were published every 12 hours for an operation I did in September in Singapore. Singapore is here. And basically, we would receive, at this period, basically, first, our quayside was extremely exposed. It's how it is. Sometimes we don't show it. It was for a loadout by SPMTs, by low-load traders. And there were a lot of squall events. It's very short burst of wind that lasts for a few minutes, but that has a very high intensity compared to the average of the day. And so basically, what we monitor a lot in Singapore typically are all these squall alerts, so that we can have people ready to check the mooring lines and not to start the operation when there are too many of them. That's what it looks like. This you can get from, weather, like Sudro company, or that they can do live monitoring of weather. In Taiwan, for the West Coast, I'm pretty sure you have plenty of it. The last point on the preparation side for the designer. So we talked here, I took the example, and you will see in the operation execution after, it's a partial chain replacement that we could took as an example, but a complete line change would basically follow the same logic, except that your assets would have to be sized to retrieve a different length. It's going to be a lot more close to your hookup asset requirements in terms of deck space, in terms of ability to retrieve the drag anchor if you want to retrieve the drag anchor. But then in terms of analysis and behavior of the foundation, it's not going to change. You will not have more analysis to do. The complete mooring system replacement, either partial segments on all the moorings or complete line for all the moorings, there, what it will include is that you will need to gain an understanding of the sequence in which you want to do your mooring lines. You're not going to do all of them, start from the one at 12, then go all around doing your mooring lines. Same as for your hookup, you have to work in sequence. So you will work on each corners, and you will work in sequence to do your replacement. So that's the only main difference. The rest, all the basic steps for the mooring replacements, they will stay exactly the same. There's no difference. And last, that was the point I was making on the preparation for installation aids, is that anything that you had required for the hookup to pull your line or to direct a pulling cable, for example, to a winch or to an offshore asset, you will need to reinstate them. So if in your original method statement, you're using an offshore crane to install your mooring, it means that it's not mentioned in this procedure, but you will need to bring back an offshore crane. Else, it means that from the start of the design of your floater, you need to include the possibility to have repairs. You need to include the possibility to have, for example, chain jacks, or you're not going to use drum winch because it's very big and low capacity. But like, for example, to include a linear winch and fields. So additional installation aids that were not used for the initial installation, where you can gain greater pulling capacity to have your mooring line in place. The problem of these high tension systems, so linear winch, strain jacks, and all that, is that they are very slow. And so that's why in your original hookup procedures, it's unlikely you would use this type of asset. So usually you would use a combination of winch and offshore external pulling or internal pulling once you basically need to do the last fueling. So there, I don't know. Is it something that you've looked already with your floater on the hookup means and the equipment or installation aids that you would need to perform the hookup? Is it something that you have already considered to develop in your foundation?
We all need to talk to the moist.
Okay. Moist?
Yes, moist. Moist also in Singapore, right?
Mm.
Yeah, yes. But we didn't decide the detail yet.
But how is because there is no detail, how is the chain connected to your fairleads? Is it like a shackle system?
Oh.
Is it like a locking system where you pull through? Have you already looked at the?
We use fairly to connect the floater, but I don't know how.
Yeah, okay.
How it works.
I don't think I have a picture here, but yeah, usually you would have a for a semi-sub system, a very traditional system is a subsea fairlead, or a fairlead that is close to the waterline. So your chain comes to the fairlead, goes up, and your locking system is at the deck elevation. So either it's an extension of the deck with like a ratchet like this, and you lock your chain inside. And after on the deck, you have sheaves and winch to basically pull and direct with a wire. So you don't pull the chain. You will have the chain, and on the top of the chain you have a wire. You calculate the length of your chain, the length of your wire, so that you pull the chain with a wire through the fairlead, then the sheaves, and you go to your winch, you go to all that. And after, there you have two options. Once you have engaged the first link in the locking system, then you have two systems. One is you come with an offshore crane. The offshore crane comes and gives you your first pretension, because you will do one, and then you come back and you do a few, and you finish with deballasting. Or you have linear pull systems on top of your chain locking system. So it can be like looks like a hydraulic jack system, which is big enough to pull 2 chain links by 2 chain links. So you pull 2 chain links, you lock, you remove, pull again, and that's why I say it's very slow, but is quite cheap compared to an offshore vessel with a big crane that can pull your pretension. Is slower, but it's cheaper. So yeah, usually you would have Fairlead and the locking system at the deck. Why you don't want the locking system lower is because for operation and maintenance, you want to have access to it. You don't want to send divers, you don't want to send ROV down, very near to your foundation. So you try to bring it as high as possible. So yeah, it's extra chain length. Maybe I can find some pictures and I can show you.
You can control the mooring line tension on the deck or on the foundation or on the AHT. Is both can.
The AHT cannot control the tension. Okay. The AHT will only be here to give and pass the chain. Can use the winch to retrieve wire and to help position the chain, but you will not pull with your AHT to bring the chain up. The chain has to be brought up either by a winch on the foundation or by a crane or something like this. So, and that's why I'm saying whatever you've defined for the hookup, the best is to make sure it can work for a repair case. So that if you have, for example, a winch and linear jacks, you will move the equipment from foundation to foundation. Maybe this is not too expensive, but the structural foundation stays in your foundation. It is extra weight, but at least you don't leave a winch here for 10 years without maintenance. Mm-hmm. So the idea is really you have the system, move it to the next floater to try to avoid the use of external vessel. So yeah, it's just that it's a matter of economics. It's if you can afford to have a heavy lift vessel for your hookup, fine, but it's always more expensive. Yeah.
So the floater has a chain to control the itself.
The floater?
Floater has a chain on the winch. So it has a winch.
Yes.
To control the.
But it's temporary. So yeah. So the winch, basically, you will have a line. There are some slides after, but basically you will have a line that connects the top chain segment, the top chain link, to your winch. The winch or the drum winch, it has low capacity but high speed. So when you need to pull a lot of chain and your wire, basically you need to pull your wire length plus your chain until you engage your first link. You need speed. You cannot do tooling. It's too slow. When you have to pay out, to take 200 or 300 meters of cables, is too slow. So that's why you would use a drum winch until you engage and you lock the first link into your stopper. Then you're still not safe because you don't have enough tension. Your foundation is here, and your chain will look like it's not a nice catenary. It's a catenary, but your touchdown point is way too close from the foundation. You don't have enough pretension. So after to create the pretension shape that you need, that's why you need to do a combination of pulling your chain links, and at the start is easy. It's only the weight of the chain plus the dead weight of the chain. At the end, you start to need to pull your catenary. You need to move your touchdown point to your target touchdown point, and that's where the load can become. We are talking about in the hundreds of tons. I don't know what's the pretension for your floater with the target buoyancy, but probably a few hundred tons. Do you know your pretension value?
400 tons.
Okay. It seems a bit low, but okay. Yeah, okay. If it works, it's good.
1000 kN.
Yeah. Okay. So basically, it means that you need even more to pull your chain because you're also having the chain weight to take into consideration, and that's where you need to find the compromise between bringing the drum winch for the speed, bringing a linear pull system to have more capacity, and not forgetting your ballast system. And that's why a semi-sub, where a semi-sub is very powerful, in my mind, and that's my personal opinion, when you have a ballast system, it's because the ballast system, okay, is no good during operation. PPI, even they stopped doing it. But for installation phase, yes, is a bit more heavy, a bit more expensive. You have piping, you have a valve and all that. But your pretension, the 100 ton that you need, you can do, basically you start your foundation, you put half a meter or a meter extra deeper in the water. You do your pulling, you remove half a meter, you have more than 100 tons of pretension on every chain. And it is controlled and the same on all the chain. So that's why it's a combination of how fast do you need to do your operation to pull, because when you're doing your initial hookup, we're not covering hookup, but when you do your initial hookup, it cannot take too long. You're always on the same thing. You have a weather window. Your foundation is being held by, let's say, 3 tugs. As soon as you start pulling the chain on one, you want to become storm safe. So storm safe is it's quantified in your foundation design. It's going to be maybe 2 mooring lines on each side. Once you're storm safe, meaning enough mooring lines with enough tension in it, you can remove the tugs, and then you have time. Then it's easy. But it means you've already done 6 mooring lines, and 6 mooring lines, and you need to do them fast. So you don't want to do, having too many winches, too many sheaves, and all that. So you're not going to have as many winch and as many sheaves as you have mooring lines. You will reposition. Basically, you can use 1 winch for 3 chains. And then once you have finished this winch will be used for another floater. But it means the day you come to do a repair, you need to do all this in reverse. And it means that the installation aid, the winch, anything that you have used has to have been maintained, tested regularly so that it's ready to work. And that's part of the thing when we are talking about the general timeline. Preparing your equipment, that's what I have put in the weeks to the day of the execution. Testing, reinstating all your equipment is going to be something that's going to mobilize people, go on board, test, so that you're ready for the operation. So yeah, so it's a combination, and that's where we are back at the discussion we had at the start on the iteration between engineering and operation. Is how much effort do you want to do on your engineering to make the life of operation easy? And the opposite, how much engineering can make operation easy by having a ballast system, by having good and smart pulling techniques, and all this. You will get some ideas from if you're discussing with Maurice. They are very experienced in all this, but that's critical points. So talking about the actual execution and going a bit in the phase. So now what we assume is that we have prepared anything that we had to prepare. The operations are ready. Everybody has signed off on the operation, and we are happy. And purely looking at a step-by-step of the operation itself. So the first thing is you bring your AHT on site. All your equipment, all the reinstatement has been done on the foundation. and you position yourself in DP mode at the target location for your ROV to reach basically the chain segment that you want to replace. So here the assumption is that we want to replace a small part. It's not the top chain. It's it's part of the top chain, but it's a small section of it. Cool. So the first thing, as we said, is going to be understanding and adjusting the balance of the foundation. So once your AHT is in place, you need to have your foundation in the ballast configuration required for the operation. As soon as you have lowered the tension in the connection at your connection point, you can send in the ROV, and you will connect with a special hook, a pickup line or a fishing line, to the top section of the segment that you want to replace. This part, this messenger line or connection line, you will connect it to a buoy to basically secure your messenger line so you can retrieve it later. The idea is that here, if you need, you can still stop the operation and come back, pick your line again, and start again. So you're not limited yet in your operation. Once you have the weather window and you've reached your go no go, in this case a go decision, the idea is you will need to disconnect. You will take back basically some tension through your pickup line with the mooring winch. So your pickup line is connected to the winch that we saw on the vessel. That will basically create some tension here, offset your touchdown point, but it will also relieve from the connection point the dead weight of the chain, part of the dead weight of the chain, so that your activity, so let's say we take the assumption that we said that the locking system is on the deck here. It was not represented, but so what it means is that with this line tension transfer, it's a lot safer to disconnect here. You will have very little load to take from the locking system, and you have no inbuilt tension in it. So you can do it with limited lifting means. So as we said, you could reinstate your original hookup system and remove the tension from the link. Open your locking system, and once your locking system is open, you pay down the mooring line so that the mooring line basically is only being supported or carried by the AHT. So that was the point on the interface, and you clarified your philosophy. But basically, you have two philosophies. One is if your chain stopper is underwater, meaning that your connection point and your securing point doesn't have a fair lead. But for example, you have a chain connector directly built at the bottom of the foundation, then it needs to be ROV compatible, and you would pick up some tension with an installation line on the foundation, open the locking system. So usually it's a ratchet that you can open, and after it's the same thing. You basically just pay off the wire to transfer the cable load fully to the AHT. So once and that's the other case. So the case where, as we said, the chain stopper is above the water, then you just open and you release through the stoppers to transfer the load via the fair lead that would be done.
Excuse me.
Yeah.
At the meantime, last page. At the meantime, we need another AHT to hold the floater position, right?
No. Ideally, what you would try to do is your analysis and the weather window that you would have planned should make sure that with the 8 mooring lines remaining, they are sufficient for the station keeping of your foundation.
Because we have to add mooring lines.
Yes.
Okay.
So basically, so that through the window of operation, the time of operation we defined just before. The idea is we need to make sure that the foundation can hold the excursion, and as we said, can hold the maximum excursion and loads on the cables. Again, it's not the same configuration as for your hookup. During your hookup, you have no cables, you have no turbine. So now the configuration is different, your ballast configuration is different. So you need to run this case, and that's why I put as a priority running the ballast case as one of the first things to understand the sequence. Yeah.
Sorry, it's Eric from CR.
Yes.
We would like to know in this stage, would the current also affect the mooring line and will also affect to the positioning of the vessel?
Yeah. So if we look on the vessel side, that's what we were describing before. When you look at your dynamic positioning capability and the rating of your vessel, you want to make sure that the orientation of your vessel with regards to the prevailing weather conditions, so it might be high current conditions if you're in, for example, a high tidal area, it can be your wind, can be your waves, that you have set the orientation of your vessel to maximize your efficiency of your DP system. So the current, as long as your combined environment remains within the envelope of your DP capability, is not going to be the problem, and that has to be studied. That's why we have put before the DP system rating study. Really, the idea is to make sure that, again, with the window of weather that we have planned, the DP system needs to stay within its capability, and it also needs to have sufficient redundancy to maintain this capability in case of failure. And that's what we are talking about in terms of rating of your DP system. For the foundation, yes, of course, the foundation is affected by the current, and that loops back to the point I was making just before, which is doing the analysis of the foundation in the 8-line configuration with the environment planned for the operation. So when it's a planned operation, you are in control of the weather window that you want to define, and that's easy. When you are in an emergency repair type of scenario, then it might be a lot more of an issue. You might have a lot more engineering to ensure that your foundation and cables remain within the design limits, because maybe your current events are at a high, let's say, value for this for the operation. So yes, it can have a significant impact. For the chain itself during the retrieval, we did mention that it is good to run a mooring or a chain motion analysis, for example, when you're doing this transfer operation, just to understand the behavior of the chain and to size the securing systems and your messenger lines and your fishing hooks to understand your load path. But the impact would be, let's say, a lot less on the mooring chain itself, especially with current.
Okay, thank you.
Yeah.
In the main request, how to monitor the water now tidal too much.
Is what too much?
How to monitor the water is not high much.
The excursion? Okay, the tilt. Okay. Again, that's the benefit of having a ballast system. For a one-line connection case, I mean, we are talking about it more in detail for the turbine integration. For a one-line connection case, it would need to be studied. Basically, what is the impact of removing the pretension and the connection of one line on your platform? I mean, your ballast system at this stage would have been, let's say, put back in service to remove some pretension on your line already. So if you have to use it to maintain the keel level of your foundation, use it. But I wouldn't make it as a necessary condition, because the impact of removing just one line pretension within your bundle is going to be limited. You will have more impact with regards to your excursion, and especially depending on which mooring line you're removing. You will have more impact on the excursion than on the tilt of the platform itself. Your vertical component from the mooring chain is not contributing as much as when you have all the environments tensioning your system. We're going already a bit above time. So next step, the idea is when you retrieve the chain just before you retrieve your messenger line, you will use your winch, and basically you will reconnect, you will secure your chain through the rollers on the shark jaws that we saw before, and you will progressively retrieve your chain until you reach the bottom of the section you want to repair. Now, what is interesting is that at this stage you will you will become independent from the floater. You basically remove the messenger lines and all that, and you can walk to a working position where you can minimize the loads in the chain, and you basically can focus on your AHT, gain some clearance with the foundation. You don't have to stay as close. For example, if you're removing a chain segment that is very close to the foundation, you can go away. And like this, you can work on it. You can help yourself with some buoyancy or intermediate buoy on the chain also, like here, for example. If you want to maintain and to avoid disturbing too much the bottom section of your chain. If you're high enough, basically you have this opportunity. When you're on the deck, basically your main activity is going to be cutting segments of the chain. That's not chain. I'll spare you the noise because it's very, very noisy. But this is no small task. So this case was it was cutting through 160 millimeter chains. Here. And basically the cutting time is more than an hour per link. So yeah, an hour 15. So it's a significant operation. That's why I was telling you all the small contingencies you can take. It works for a single operation, but when you will have to pile up a full system removal and all that, you will need to quantify, and that was to take this example, the operation specialist, they will have to quantify down to the hour all these steps. You don't want to take unnecessary contingencies that will impact your operational window and then make that you have to take even more contingencies for weather. So that's an example of the chain cutting. Here, it's offshore H links. Is that once you have cut a chain, you separate your links. You need to reconnect your studdless chain with the bottom. The one solution is usually using this kind of H links. They do behave differently, but they don't have the same weight first. And then obviously there are mechanical components. So you have pins, you need to understand them. And this needs to have been sized and procured as you're preparing for the operation. One thing to take note when you're doing this operation is that the chains, you have a criteria in terms of number of twists when you're doing your hookup. You have a number of twists of your chain, a maximum number that is allowable or that is allowed on the chain. You cannot have all the links basically locked against each other. One critical thing is that when doing all these operations on the deck, you have to monitor that you're not twisting your chains so that when you will put your chain back, you're back to the same configuration. And when doing your handling of the chain, that's going to be critical. You are not going to be able to just hang your chain and let it swivel around. That would be problematic. Did I skip one? No. So once your chain segments are in purple, now we assume the new segment is in place. the idea is that you will need to do the reverse operation. The messenger line that you had either left on the floater or on the HT side, you need to route it. So ideally, you leave it on the floater. It is routed through your bottom fair lead, as we said. So now we assume you have a bottom fair lead, and your top stopper, your deck stopper. So you will need to bring this messenger line back on the HT deck, connect with a shackle or lifting edge the top chain of your segment, and you control the position of your chain and basically the deployment of your chain with your pickup line and the position of the HT. So you will bring back the HT close to the floater, and you will pull the messenger line back on the floater. So in this case, you can see it's this kind of case where I was telling you, if you have a temporary winch that was used for hookup, that's where you need the ability to pay in large lengths of cable or long lengths of cables. And that small linear winch, for example, won't make it there. And once your messenger line is passed, so here it's represented because we had assumed in the drawings that you had a chain connector at the bottom, but you imagine that your bottom fair lead, basically the chain is going through, the chain is going until the stopper at the deck level, and once you have your chain which is back and engaged into the stopper, you can release your pickup line from the HT, and you can release the messenger line. So you use the ROV to disconnect it. One thing is that the ROV should do the survey of the chain before you finalize the installation. Should do the installation of the chain, a survey to check that it is still following your target touchdown before going further into the operation. And then, as we said, you need to reinstate some tension in your chain, either via mechanical means like linear jacks or your winch, but mostly through your ballast system. And then you're done with your operation, you can demobilize your AHT and your replacement has been done. I'm sorry, we are 13 minutes late on the schedule. I should have trusted my initial judgment on the duration. So thanks for your contribution during these slides. Any additional questions? We have a bit of time. Is there? Yeah.
You just show the broken section is upper, is at upper.
Yeah.
But it's different between the upper and if you want to repair the bottom line. So
it's going to be more complicated if you have to repair something that is typically below where you have your clamp area and your touchdown area, because then you have to make a decision between doing subsea cutting of your chain. Basically, with 60-meter water depth, you can very, very simplistic way, you can retrieve a part of the chain and bring it to the surface, but it means that you're going to pull and create a double catenary on the two sides to bring back to your vessel. So the loads are twice higher than what you're trying to do here. You're basically creating 2 times a 60-meter catenary on each side. And also means either you're going to have a catenary that's going to reach your anchor side, which you clearly don't want, or you're going to reach your touchdown side, your clamp area. So usually, that's what I was saying before, you would favor underwater cutting of one of the section that you can retrieve, and then you can basically retrieve on board, do the change out, and install it back. That also means that the ROV that you would use would then become a higher work class of ROV, because you will need to be able to handle subsea component installations. And these subsea components, they are designed to be ROV operated. So you have ROV operated H-link, for example, but it is an even more complex mechanical component and a lot more costly also. So then, I would say more cost-effective solution is actually to retrieve the full mooring line. rather than trying to just replace the bottom segment, is to plan to have an AHT with sufficient deck space to lay up your chain from the top to the segments that you want to repair, even if it means removing the drag anchor and reinstalling on a new anchor point later. The complexity of running a subsea operation for chain repair, it is doable. I mean, people are doing it, but it has a significant cost impact compared to just retrieving the chain. And, yeah. So after, it doesn't mean that you have to trash the whole chain. You can replace just the segments that you have, but it will require to perform a new complete chain installation and anchor installation, which then triggers the need to have a slightly bigger AHT, because you will need to vary your drag anchor again, load test your drag anchor again. So that's what we had on the first slide about the options for the AHT. Usually, you would be back to the asset you have used for hookup, rather than a smaller AHT for the line repair.
Let's just say that the operation is more complex. You will have to decide whether you want to transition the whole line or repair.
Your lines are not, I mean, 560 meter is not considered very long. You have very big links, but it's not an extremely long mooring chain. We are seeing offshore facilities with chains that are laid over a kilometer and more. And in the same way as you can do the installation of these chains using AHTs, and you can either have single bundle of chains or joining chains offshore. Yeah, it is an operation that's being done quite widely. And obviously, today you're using drag anchors. If tomorrow you're using suction piles, driven pile, or drill pile, which are clearly you don't want to remove them. Drag anchors have the beauty of you can remove it. It doesn't cost a lot in terms of asset, and it's just a reverse operation to put it back. Just you need to choose another location. Then obviously it will change your philosophy. And in these events, we see people. I mean, we see operations where you abandon the chain that is damaged or broken. You retrieve what you can. You leave the buried section, basically, if you're allowed, and the anchor point, and you install a new anchor point and chain.
So our design have the clamway. So because clamway is on the bottom of the marine line, so clamway didn't change the procedure, whole procedure.
Yeah,
I have a question. I want to know the mooring system have the load cell. It's in the chain stopper or BLD.
The load cell, you have a lot of technology, a lot of unreliable technologies, I would say. There is not a single solution that has imposed itself and that has been widely adopted. I mean, I've seen it a lot on offshore oil and gas tensioning systems. We are still seeing it on foundations. You can have like a pin monitoring. So, for example, directly in your chain stopper, you build your hinge pin with load cells, and you take the load from here. You can have indirect monitorings of tensions using inclinometers or underwater. It's not really a sonar system, but basically it's the objective is still the same, is to measure the relative inclination of your departure angle of the chain with the floater and have a back computation of the tension of the chain. Then you have some inline tension system that you can put on the top links just below the stopper also. They are extremely I would say extremely unreliable, but it's basically just strain gauge technology and strain gauge technology underwater. I've seen more failing than succeeding. So ultimately, the thing that is being done is, and especially now with digital twins, it's a lot about indirect measurements of the tension. I think that is becoming the more reliable solution that is being adopted, and it is actually cheaper. So yeah. I think it's good to have, like, for example, monitoring pins on small scale projects, projects where you want to gain a better understanding and you don't need to have something that's going to last for 15 or 20 years. But at least you can accumulate enough data and direct data from your pin measurements. But for an industrial model where you intend to do 25 foundations, my personal opinion, I don't think that would be the way to go with direct measurements. And maybe in a few years there will be better direct measurement systems, but today it's fairly unreliable. Thank you.
So which have you decided what kind of connector you want to use?
No, not yet.
On the deck or below?
No,
below sea level.
Fairlead
Yeah.
and stopper on the deck.
Okay.
For now, that seems to be the option that is being discussed.
Fairlead and stopper without ratchet.
Ratchet on deck. I mean, that's what I was saying, that ideally in terms of maintenance and in terms of ability to intervene on your mooring system, keeping the locking system at deck level or at least accessible without going underwater, it is more favorable O&M option. Slightly more expensive, a bit more chain. Yeah. Let me just check. 11:10. But if you want, there is we had planned to start the next one in 10 minutes. So if you want to have a small break, I need a water break.
Okay.
But else, yeah, if you have some questions or anything, I'm happy.
10 minutes break. 10 minutes break, right?
Yeah.
Yes. Okay.
I mean, if you need 15 or more, you take.
Then, DR, are you ready to start? No answers. Hi, Hayosen.
Yes, we can start. Thank you.
Okay. So that was the mooring part. So now looking at a very different topic, very different for a few reasons. The first one being the level of maturity of it. You will see it's while the mooring system is something that has a lot of track records that has been done on various assets way before floating wind foundations. Looking at floating to floating wind turbine installation is a far less mature topic. So there are still a lot of open questions, and we'll still try to explore and answer some questions on that. But we'll go through the same path, meaning looking at the stakeholders, timeline, and selection of assets, the different steps and the main steps in terms of operation preparation, and then the operation execution slides, drawings, as we have done just before. So first, in terms of key stakeholders, I have put the foundation designer as number one, and you will see there are many reasons for that. We also have obviously the turbine OEM. They will still play a very significant part in the operation, and transportation and installation contractor. The scope can vary. We say transportation and installation usually because we associate the fact of transporting the components of the turbine on their asset or on some feeding assets, and we are, let's say, more looking at the installation asset itself, which is the one with limitations. Last one, MWS. It is an operation offshore that would usually be subject to review or comments of third parties because of the stakeholders and because of the coordination of different, let's say, high-stake stakeholders, especially the OEM and the foundation designer. On the right, the picture is the TIA Herema heavy lift vessel. It doesn't look like this, but it's actually a 3D representation that comes in their methodology for floating. So that's actually one of the stars from that they took as an example for their lifting case. If you go in their documentation, they've also done an installation case for CLP. That's quite interesting to look at. There are lots of GIPs and research group working on these topics of floating to float. Same chart as what we discussed on the mooring installation, and even more here. The problem is that today regulation, rules, specification, and standards, it is understood. We know the environments. We know what we are operating in. The overall planning has a lot more unknown than what we have in the mooring case. The reason being is that there is little, if no, for floating to floating on this range of turbine, a return of experience. So an overall planning and the ability of a contractor to define a proper planning sequence comes from their experience. It comes from their return of experience. So this point today is having a bit of a question mark, especially because you will see it is tied extremely closely, and the impacts in terms of engineering to operation choices can even have impact on the overall planning of the operation itself. Design brief, design basis are fairly well understood, and then same loop as the one we were defining before, engineering together with the operation procedures. Again, where you could benefit from a lot of early feedbacks from an operational procedure point of view, let's say from the installation contractor for the mooring, for example. today, they will give you feedbacks from bottom fix installation offshore with vessels or jackups vessel. Some of them can give you, and other, let's say, contractors can give you feedbacks on integration of turbines at quayside on floating foundation. That has been done. There is a start of a track record of this kind of integrations. I don't count the spars that have been basically the turbines that have been lifted on the spars. I don't really count them as floating because they were secured at they were not fixed. They were secured in a near fixed position. So there was no motion basically, and it was a lot closer from a bottom fix case. But so it means that at very early stage, the loops between operation and engineering are going to be quite laborious. They are going to take a lot of time, and we will see that it will have significant impact in terms of weather restriction, but also in terms of installation aids that will need to be defined, and the additional calculations that have to be done to make the operation happen. Here, we are not talking about timelines that start a few months before. We are talking at least a year before to plan this kind of operation, if not even earlier. When I talk about a year, I'm not even accounting for the actual availability of the vessel that can do the operation. We will see after. The number of assets that have the ability to do a floating-to-floating lift on a floating foundation in the range of 14 to 15 megawatts are extremely, extremely small. There are not many. You can probably count them on one hand. That means that when floating wind, if floating wind comes in competition between different floating wind farms, there is going to be a battle for these assets. And these assets today, they are built not for floating wind. They are built for larger bottom fixed foundations to install a 20, 21 megawatts type of turbines. So it means that actual contracts, when we talk about contracting of the contractor, which is the first one that should come, here I put within the year, but maybe these assets, they'll be booked for, I don't know, 2-3 seasons. You are in the same hemisphere as all the other big wind farms, meaning that if you are a floating wind farm in Europe, they will compete with for the same season of installation as you, meaning spring and summer or early autumn here. They are the same. So you don't even benefit from having an offset there where, for example, if I was installing a floating wind farm in Australia, well, it starts to be a bit of a journey for the asset, but ultimately I could make use of assets during a downtime in Northern America, Europe, or Asia installation sites. So that might be one of the struggles is to find the asset on time. And we start operation engineering within the year before. It is something that would have to be triggered very early. And we need to complete all this engineering not weeks before, but months before. Because the quantity and the need of fabrication of dedicated installation aids or specific items that we will need to design for the integration of the turbine for floating to floating is going to be a lot greater than what we had to define for the mooring. So that means that the foundation designer, the OEM, and the installation contractor, they need to have aligned their engineering months before the operation. Then, in the weeks before, it is more, let's say, normal operation. It's about getting approval from the MWS for the area that they would have to either witness or survey and approve. It's about mobilization of the vessel and installation of all the temporary items on the vessel. So typically, it's going to be the sea fastening, the grillage of your turbine components. It's going to be the makeup of the crane. So typically, a crane on this vessel, they don't have a single configuration. They can have different boom configuration, boom angles, jibs. So you basically need to take around a week and a half to just configure the crane for the operation that you want to do. In our case, typically, we are a lot more limited by the hook height, we'll see after, than the actual load capacity of the crane. So it's likely that you would need extended jibs on the crane to reach the hub height that you target. And if this extended jib doesn't exist, they need to build it for you. So yeah, we prefer not to have to build it on the project. It's expensive. And then within the days before, same as what we said, it's about getting ready for the window of operation to open. It's about securing the components on the vessel, making sure that the team is mobilized, and you can start to transit to the installation site. These assets with the turbine components, they can actually take a fair amount of weather. They don't have to stay at quayside. They can be in standby offshore. The sea fastening and the degree edge of the components are robust enough for that. And same as for the mooring, we will need dedicated and specific installation aids on the foundation side. But not only, also intermediate step after. But anything that can be pre-installed and prepared on the foundation, it can be temporary access, it can be containers with tools and scaffolding, it can be temporary installation aids that you have to weld on the foundation. If it has not been done when the foundation was sent offshore, you have to do it then. The main asset that we are looking at, obviously, is the offshore installation vessel. The main, let's say, factor to decide on the vessel that you want to contract, it's the crane hook height and the capacity and the radius that you need. So it's about how high can you lift, how heavy, and how far. Knowing that the how far, basically, the closer, I mean, the smaller radius you can lift at, the closer your asset will have to be from the foundation. So you try to be not too close, but obviously you will see, there's an example of load curves after. The further you get, the more capacity you lose on your crane. That's the first and actually biggest limitation, the crane hook height. And we measure the hook height from the deck. So you will see in terms of number, when you look at the hub height that we have, which is around probably 140, 45 meters, you will need to keep that in mind, that you need to add the vessel freeboard. Motion envelope during lifting operations, if you can, because I think at this stage it will become a luxury, we prefer to take assets that are as stable as possible offshore. I'll take a very extreme example. You've seen on the previous slides the TIAF from Herema. It's a very wide semi-sub lift vessel. It is obviously a lot more stable and less subject to motions than, I don't know, the Deme Orion, for example, that you have here in Taiwan, which is a monohull standard vessel. When I say it's a luxury of choice, is that today, we'll see after, there is not so many assets, and the price of these assets are so much that you probably won't be able to have the luxury of choosing this thing. But just to keep in mind, there are assets that are more sensitive to motion than others. And here, the floating to floating turbine installation, you will see everything sums up around the control of relative motions between your foundation and your turbine components. You will see that we can do with motions, obviously. The motion envelope that are given by OEMs are today extremely small, what they are ready to accept. So OEMs will need to re-engineer and rework their components to have, let's say, more allowance in the motion and the relative movements between the parts to make it work, because floating to floating won't work if that's not being done. Availability and day rates, again, if you have to do it, today your floating to floating case is basically in competition with doing a lift at quayside. Today, it's a lot cheaper to mobilize a crane, like even the big Sarengs 13,000 crane or the very big to do turbine integration at quayside in a more controlled environment. That's what you're competing with in terms of day rate and availability. Now, discoupling the turbine integration from the floater installation is obviously getting closer to the monopile and the bottom fixed installation methodology, which is interesting because then you can install all your foundations and then install your turbines. So that's all to be weighed in when looking at availability and the rates of these assets. As I said, the primary objective is the hook height of the vessel, and capacity will follow because the assets that are available today with the hook heights we are talking about, they have the capacity. That's lesser of a problem. And today, the limits that we have reached on the bottom fixed side is 160 to 180 meter above deck. That's the biggest installation vessels that we have today to install turbines offshore. Knowing that some of these assets that can lift at this height, they are jack-up vessels. So it's a bit cheating because their hull is not floating. Their hull is on top of their already very tall legs. So while they are able to lift at 180 meters, it's in a case where they are probably around 20 meters or 15 meters above water, which is very different from a floating to floating case where you don't have the luxury of having jack-up legs. So that's why we need to be very careful. And that's just to highlight that in today's configuration, what you're aiming at in terms of floating to floating on a 14 megawatts on a foundation that has its own freeboard and all that, we are already looking at a hub height we said earlier, which is probably around 145 meters. So we can see that we are, without considering the specificities of floating to floating, we are already near what we are doing and what we are trying to achieve on bottom fixed today. So that's why I'm saying it's a very it's much, let's say, at its infancy and at the very start of looking at these assets for this application, because it is actually something that is just being the bottleneck on bottom fixed now. So taking an example of the different, let's say, parts, but that's a lot, let's say, it's a lot more straightforward. But in terms of asset selection, when you look at the asset, the cargo deck is obviously something that we want to look at. It is your ability to carry your turbine components. But again, because you have a very big crane on board, it's very straightforward. If you need to have a feeder barge to bring in the components, it is being done on offshore wind farm today. It's very standard logistic. So it is less critical. It's not as critical as for the HT, where we're trying to limit the number of assets, and we had no big cranes to help us. But here, cargo deck is basically your workspace and your storage space. Accommodation still the same. If your heavy lift vessel is the asset to, let's say, run the whole operation, you need to make sure that you have sufficient accommodation for everybody involved on the operation, and that means turbine side, foundation side, and installation platform. Then propulsion maneuvering, same as for the mooring. It's going to be even more critical. You're going to work even closer from the foundation. You want to maximize your lifting height, you need to minimize your radius. Basically, the more vertical your crane is, the nearer you are from the foundation. So your control in terms of DP has to be third class, which is a good thing because all these newer assets with very big cranes, except the older generations, oil and gas, semi-sub and all, they all have DP3 ratings, so they are able to operate very near the foundation. But again, it is a very important factor to consider. And last, obviously, the main item is your deck crane. So the deck crane, which is characterized by the hook height, lifting radius, and capacity. Now, looking at the state of the market and what we can actually look in terms of assets. So there is only a very limited number. So it's not an exhaustive list, but it starts to be let's say significant enough that it is representative. This is a combination of let's say oil and gas type of assets. So you have the Sleipnir, Aegir, the Pioneer Spirits, Saipem 7000. They're all assets that were developed more for oil and gas operations. Extremely high lifting capacity at 10,000, 5,000. This is a converted hull, 12,000, 7,000. So obviously, when we look at our package, they're all a few hundred tons. So we are in overcapacity. But what we need to see is that if you lift 10,000 on the main hook, here it's only 105 meters above deck. That's not enough for us. So you need to use, and this one is just at the limit, you need to use the auxiliary hook, which brings you to 145. That's why I was telling you, all these cranes, they can be mounted with additional booms, additional jibs, that gives you either auxiliary hooks or a greater lifting height. And then you lose 25% of the lifting capacity in this event. And 145, I kept it, but today it's really just the limit of what we need. It's your hub height. On your hub height, you need to include rigging height, spreaders, lifting, when your rigging, and so all this will basically bring your actual minimum required hook height to another 10 to 15 meters. Because you will have a spreader bar, you will have all this equipment. Obviously, this limitation only applies to your last components. They will only apply to the RNA and the blades. For the towers, you have a bit more flexibility and a bit more room for your lift. But if we keep on going through, what we see on the bottom, so Asian Hercules 3 is a bit of a special one. It's a barge. It's a shear leg barge lifting. It's not really done to operate offshore or very far, but it is a very stable platform for lifting. They have a bigger jib than 120. Yeah, they have a bigger one than the 38. The rest of the items, they are the newer generations of vessel, or let's say more recent, and they were developed with the bottom wind turbine installation in mind. So these vessels, they all have a much higher hook height available and a lower overall rating compared to the big oil and gas assets. So obviously, the ones that are going to be available for us and that are going to be the most relevant, they are these wind assets. They are the most stable. They are the ones with the better DP system and all. So if we take, for example, the Deme Orion, or even so the Deme Orion is today the asset with the greatest hook height, 178. There is one, so not many to do, but that would work. The Green Jade, for example, with the auxiliary hook on the extra jib, 185. So there are assets today that physically, in terms of geometry, can do it. It is something that is possible. And it's just that today, the market is focusing on bottom fix. They are not developing assets that are for floating to floating. So the contingencies that you have in this capacity, they are considering a lift from a floating platform or a jackup platform when there are jackups to a fixed foundation. And that means that the dynamic amplification factor, the additional contingency or the derating that you put on your train curves is not applied. So when you look at 1005 for fixed to floating, for floating to floating, you might already lose 50% of this capacity just because of dynamic amplification. I mean, basically your dynamic calculation. You're not going to use just a DAP factor from a book. You will do actual, and we'll look at that after, but you will do actual couple motion analysis to understand how your lifting system is working and how your system is responding to motions, so that you can size your rigging and choose your vessel accordingly. But that means, and that's the whole complication, is that all these assets, they are very different. Their hull shapes are different. Their cranes are different. The geometry of the crane is different. Some of them, they have a hinge point at the deck. Some, they have big pedestals. And that means that the assumptions you're going to make early in the project, when you want to start working on floating to floating scenario and your calculation in terms of dynamics, they will be heavily impacted by your assumptions of vessel. And you cannot do just an envelope calculation, hoping for the best, because there are so little assets that you will need to make it specific to a vessel. And that's the whole complexity of it, is that today there is not enough margin to make a conservative design for floating to floating. But it means that the discussion in terms of contracting and having this iterative loop between engineering and operation has to actually happen very early. And that's why I was putting it into, we're talking about a year or years before the operation, to have the time to find the right assets and understand the dynamics of the loop. So a representative one that would work, that was shown in the list, is the green jade that's here from Deme. And I talked already a bit about that, but the main issue that we see is because of the wide range of vessel types and the performance offshore to do floating to floating will differ, will heavily impact your assumptions when you're doing your engineering. So today, in a nutshell, there are very little number of vessels that can do the work, and it actually has to be checked. There is no base case for it, but it is something that's going to open, and basically tagging on the operation and maintenance of bottom fix on the much bigger platforms, like for example, the 21 megawatts or 22 megawatt turbines on bottom fix. The assets that have to be developed to do the installation of these turbines and the offshore operation and maintenance, they might fall actually in the range of capacity that we are looking at today for 14 megawatts. Now, I'm sure that when your floater, you will, basically it comes to a phase where it has to become applicable to an industrial case. You will be asked to scale up your floater from 14 megawatts to 21, 22, 25, who knows? I mean, we are only seeing it going up and up. And that means that the race of having a bigger turbine on your foundation will create a difficulty for you, I mean, for floating designers to catch up on the assets that are developed for bottom fix. So until there is actually a credible market for floating, the assets, they will keep on being developed for bottom fix. And you won't have enough margin, as we saw just now, very little margin to actually use these assets for floating to floating. So it is a critical point today, the availability, and it is the reality check on the fact that today nobody is investing in floating assets to do floating turbine installation, especially as the floating turbine are still pushing in terms of size to get bigger turbines, bigger foundations, and so on and so on. It is a complex problem. So that was for the stakeholder and the timeline and the criticality of this preparation in terms of timeline. Now, in terms of actual preparation and the steps for preparation. So again, the data flow, I mean, the foundation design will be a full part in the ability to do this floating to floating installation. You need to have your ballast system and the understanding of your behavior at the different step of the operation with your ballast system, because as you are putting more of your turbine components, basically, you need to play with your ballast system to compensate for the additional weight and the center of gravity shift. So how much do you want to adjust your ballast, or do you want to start, for example, with a deficit of ballast on the column with the turbines on the turbine side, to have limited adjustment of your ballast during the operation? That's a way of doing it. So all this logic and how do you intend to manage the asset during the installation has to be completed. And because you're going to be so sensitive to motion, all these steps, they will have a critical outcome in the behavior of your floater. So you would have defined an environment where you expect to operate in terms of wind, wave, and currents. You want to be able to meet your envelope in terms of mooring forces, to be okay, the cable, as we talked before, but also the global excursion of your vessel, of your foundation. You don't want to be in a ballast configuration where basically your excursion, the excursion of your foundation, could risk to hit and to get too close from your installation asset. So understanding this weather limitations and then setting them, and being working together with the T&I contractor. So the responsibility can be split or it can be done just by one party. But basically, in developing couple models, motion couple models between the foundation for every step of the installation and the installation contractor for their own vessel, we can imagine solutions where we actually physically couple the two. If we were, for example, to find that there is no weather envelope where we can meet the motion criteria, you might have some tieback, for example, from the foundation or the turbine parts to the installation vessel. So all this will need a lot of collaboration, a lot of work between the foundation designer and the T&I contractor. The main objective of these two parties is actually to satisfy the OEM, the wind turbine manufacturer, motion envelope. And that's actually the most important, because it's not the motions that are detrimental to the foundation or the heavy lift vessel. It's the ability for you to have operators guiding and coupling the parts offshore. So you need to align them. You need to have proper guiding systems. We'll see that after. And there are some components. Today, you can imagine columns are fairly straightforward and they are fairly well understood in terms of guiding and how do you assemble them. It's basically flange connections, so it's quite straightforward. But I can give you an example on the PGL floater. So Siemens is also the one doing the turbines. The turbines are a lot smaller, 8.6, 8.5 megawatts. The foundation was a TLP, which is in the configuration at quayside is extremely stable and moored in a very stiff configuration to the quayside, so very limited motions. The window of motion that the OEM, that Siemens was giving to SBM for the integration of the RNA at quayside was 15 centimeter by 10 centimeter. So you could not afford to have, when you were inserting the RNA around the top section of the column, you couldn't have more than 10 centimeter movement, relative motions between the two. And we're talking about a case where it's a land crane on the quayside and the foundation is very stiffly connected. And it took weather conditions that were basically with no wind, no wave. I mean, basically trying to be as static as possible to meet this criteria. And the limitation is not coming from the fact that they don't know how to lift and position it. It's only that the construction of the RNA from Siemens doesn't allow physically for more than that. It's not that they don't want to approach, it's just that the way they are built, the flange is inside the RNA. And if you exceed 10 centimeters, you break basically the structure, you hit the structure of the RNA. So the OEM today, their turbines, they are meant to be integrated. First, they were meant to be integrated onshore, then offshore on bottom fix, where they have developed sets of tools with the TNI contractors to control the position of all these parts. But when you do from bottom fix to from a jack-up lifting vessel to a bottom fix, the relative motion is basically just the external forces on the piece you're lifting. So it's a bit of wind, a bit of dynamic amplification on the boom error, but it's fairly small. And so they have developed the design of their turbines to be compatible with this kind of motion range. Today, if you were to be able to, if you were to enable offshore lift floating to floating, you would need to change the interface and the kind of interface that the OEM are giving. Because their interface, they would need to be able to allow for a lot more relative movement between the parts. And after, it is up to the TNI contractor to guide the part to make sure that the parts, they fit and you bolt and everything goes well. But you cannot have an OEM that today comes and say, I need to install my blades on floating to floating with a maximum of 10 centimeters relative motion. When you're 150 meter hub height or 145 meter hub height, 10 centimeter in terms of what it is, in terms of inclination of your deck, of your keel level, is nothing, it's negligible. It's not something that you're actually controlling. You have the smallest wave passing, the response of your floater, even with its mooring, you will have a greater displacement than 10 centimeters at the top. So that's the whole complexity of it, is that the OEM today, they hold the key of designs of turbines that are not suitable for floating to floating. Then we have offshore contractors that don't have assets that are designed for floating to floating. So it is really a uphill challenge. So what remedies we can do to make this happening and preparing, especially on the foundation side, is basically developing smart guiding strategies, smart installation guides, installation aids, tools that will help to locate and position the components and couple the components. So typically, you would look at lashing columns together. So once it's basically lifted with the cranes, you don't want just a few people on the foundation holding a tagline to control the position of the column. I mean, that's not going to work. You will need smarter systems to help you guide. You might need mechanical assistance to actually guide you and bring the parts in position. What we can see in this one is there are tools today that are being developed. So typically, when you look on the right, the pile grippers that are being developed, even for bottom fix today, they do have a bit of heave compensation and motion compensation built in. But basically, the idea is to tell ourselves that to enable floating to floating, we will also have to will be enabled, by the creation of specific equipment that will be sized for floating to floating. So it can be new generations of pipe grippers with motion compensations. It can be same for the spreader systems for the column lifting. And as we said, it might mean also to have some tethering between the parts and the foundation itself, or the parts in the vessel to control more of the motion. So that's a scope that overlaps with the OEM and the WTG OEM. In their responsibility, I mean, they also have to make sure that their components, they can take the transportation conditions and all that, but that's no challenge in the way that it is being done on bottom fixed. There is no challenge to do it. It doesn't change anything to do it for floating to floating. As I said, the tools, they will have to be adapted between the WTG OEM and the TNI contractor. They will have to adapt their guidings. They will have to adapt their tools for lifting. And early in the project, there need to be an agreement in terms of what are the motion and the position criteria that we will use, because setting this limit, if tomorrow Siemens tells you we can do with a box of 25 centimeter by 25 centimeter, because physically that's what our component can take without breaking it, then you will go back to your motion calculations. You will go back to defining your environment and what is the environment that you need over what period of time to perform the operation. So we will have to go backward, basically, starting with the requirements from the OEM, going to how the TNI contractor can comply with it and what weather limits it means for them to. The installation contractor, they will be the one usually holding the responsibility of the operation execution. So similarly to what we talked about before, they'll be the one providing the coordination effort and providing the general procedures, the general planning and methodology that is required for the operation. It doesn't mean that they are going to define everything on the OEM or everything on the floater side, but they are the ones bridging everything together. So that's the usual setup. They have a few of the things to do, obviously, in terms of procedures preparation. Again, we talked about planning a proper schedule, planning the operational envelopes and the weather window strategy, management of change, task plan, and as it as up. That's the more generic approach. So it is a lot of preparation from their end, and that's why their engagement needs to be very early in the project. So when they have selected their vessel, what I was mentioning before is that that's a crane curve from the statement HMC. So how you can read it is so you have 10,000 tons here. That's the main hoist. So the main hoist can lift 10,000 tons. Here is the radius at which you're lifting in this direction. So here, physically, because of the size of the crane itself and the pedestal, you cannot lift anything below 25, 26 meter radius, because that's just the volume of your crane from the center line of your crane to the, let's say, the most straight up position of your boom. Your hook is already at 26 meters. So then you maintain your top rated capacity over less than 20 meters, 15, around there, 16 meters. And then as you increase your lifting radius, your capacity basically only goes down. If you try to lift at 80 meters, slightly more than 80 meters, your capacity has been derated to 4,000 tons from the 10,000 that you had at the start. So in this case, because of the geometry of the crane, it is quite a steep curve. No, not all the cranes are built the same way, so you will see the crane curves, they have different shape, but that's the general shape that you would find. And again, this one shows you the load curves for the Sleipnir, which is a floating asset, to a fixed asset. So, for example, they are using this curve to lift a top side on top of a foundation. If they have to lift from the Sleipnir onto a floating barge, for example, so the barge has its own motions, then you have a derating of these capacities, which depends on the definition of your dynamics. So either you calculate it yourself, or you take a safety factor called DAF, dynamic amplification factor, that basically will derate your capacity. Again, for us, as we said, the capacity is not really the problem. We are lifting light loads, fairly light loads. But the understanding of dynamics is obviously critical. And same as for the mooring, the ability of the vessel to maintain its position also impacts your ability to select your load curve. When you have, for example, here in a 5 meter, you lose nearly 1,000-ton capacity when you're in this range of radius. You can imagine how critical your positioning has to be. So again, because we are lifting lighter loads, we have less constraints, but it will apply the same. If we are given an asset that is sensitive with a very steep crane curve like this, when you are at the maximum lifting height and capacity, you will have to control your position, not only because you don't want the crane to go into the foundation, but just because it impacts your ability to hold the load and to take the load of the component. So still on the installation contractor, so we talked about sea fastening. So that's a feeder case, which means it's a case where the turbine components, they are not stored on the lift vessel. They are stored on a dedicated feeder barge, so it's a flat top barge usually. So this concept was done by TWD a few months ago. So the components here, basically we can see they have pre-assembled some of the column. It is something that can be considered also because we have margin in terms of capacity. And we are trying to reduce the number of operations and the number of interface where we have to manage motions and guides. Pre-assembling your bottom sections of towers, because you're fairly near, your marshalling location is fairly near from your site, it enables you to have this configuration, but maybe that's going to be weather restricted. You cannot go unrestricted in the middle of the ocean with this. Your sea fastening and your tower would be over-designed for that. So, but because you are half a day from it, you can stay in sheltered condition, release your cargo when you need to have it come on site, have it available 12 hours later, and lift it. So it is interesting concept in your case, and it avoids the heavy vessel to have to come back to port to load the turbine components. Especially while for an AHT, it is not very complicated to shuttle from a marshalling location to an offshore location. For a large installation vessel, you can imagine the logistic is not the same, the cost is not the same. So if you can keep it offshore, is a good thing also. Again, it will depend on the number of foundation and turbine that you want to install. If you're only aiming at installing one, no problem, put everything on the deck of the vessel. If you're installing 20 of them, you have to develop a supply strategy for your vessel. So that's a point that we covered before, but basically when you're in a transportation case, you are also subject to weather, and you can choose to be more or less restricted. For example, if you want to be able to stand by this configuration offshore near your site, and that you want to be able to stand by for 5, 6, 7 days, obviously you will need to be able to take a higher return period on your cargo, and that will have consequence on your possible cargo reinforcement, but mostly sea fastening and grillage of your items. And then when looking at the actual lift, obviously we covered the first half when we were talking about the foundation designer, but the understanding of the coupling between the lifting assets and the foundation, well, I took an example of bottom fixed foundation, is important also. And last, on the installation contractor, they will usually be the ones in charge of developing all the installation tools, at least the guiding philosophy, anything that is temporary, either welded to the foundation or within the turbine component. Usually they will be the one doing it. More specific mechanical tools like blade grippers, spreaders, they can be supplied by the OEM, but they will be operated by the TNI contractor. It's more that pipe grippers are today so expensive, or blade grippers. Yeah, blade grippers, sorry. They are so expensive that usually they are built for a specific range of turbine components, like column diameters, blade size, center of gravity position, and all that. So rather than building new ones all the time, usually they come and they can be supplied by the subcontractors for the operations. And yeah, one point, they will be in charge of the safe access. So basically, it is easy to have access to a foundation when you're doing the bottom flange, but you need to maintain a safe access and ability to work when you're at the top of your first component, and so on, up to the blade integration. It is something that is taken into consideration and is being done in bottom fix. Today in bottom fix, they bring the personnel from the ladders. Basically, the access is already here, so they bring it from the ladders, and they're working platforms at every flange. In floating wind, the motions, as you get higher, you will have what's considered comfort criteria and intellectual work criteria in terms of motions, and they will basically limit. So we were talking about the physical limitation in terms of motions and movements between the parts, but the same criteria, they have to apply to the operators also. The operator who is at the top of the last column section waiting to receive the RNA, for example, or waiting to receive the blades, will be subject to motions. Obviously, the foundation is moving, the column is moving, and there is a limit at which we consider that the operators, they go from a comfort level to a level that is threatening their intellectual ability to execute the work properly. And these limits, they are fairly low, actually. We are talking about, I mean, in terms of accelerations, we are talking about continuous, like 0.5, 0.6 meter per second, like oscillations. Typically, you can take it for 5 minutes, but when you have to work and you have to be ready, guide a part for an hour, bring in equipments, talking tools, and all that, these limits, they can apply fairly quickly. And it is something that has to be taken into consideration also when developing your procedures and your safe access. And that can impact the weather window, meaning that you might have to stop your operation, waiting for more favorable environment for the last component lifting. Maybe for the first one, there was no problem, but for the last one, because obviously your motion is greater as you get higher, you will need to wait more or reduce the weather window. The last one is MWS. It will depend on the stakeholders. Usually they are, let's say, it's a convenient party to use as a third party to monitor, to survey, to do inspections, and basically to give the stamp of approval. But MWS ultimately, they cover risk towards insurance. So they will audit the project, they will review the documents. But if the project holder decides that they want to do without them and that no other stakeholders is asking to have an MWS on the project, it is not mandatory. If everybody agrees that they will manage the risk in another way, there is no need of an MWS. But else, if an MWS is involved, they will be involved from very early stage on document review, and then they will provide services for inspections, like checking certificates, for example, of mooring components, lifting components. A suitability survey would apply to the assets. So typically, they would go and inspect that the DP system of your vessel is properly maintained, that the DP rating is correct, that the documentation is up in order, and that they will not make sure that there is no breakdown, but at least they will minimize the likelihood of a breakdown by reviewing the documents of the vessel and saying, okay, it is properly maintained, it is safe to operate, they have good track record, and so on. And then they will act as operation witness also. So they can act as a coordinator sometimes. So in this example, I told you that the installation contractor would usually take the lead. The MWS can also act as, and they can also provide, for example, what we call a commander, which would be focusing on a loadout operation or on a lifting operation. And they will not develop the procedures, not develop anything. They will only be here to provide the coordination effort and get everybody talking together at the right moment. So they will basically instruct the installation contractor, the OEM, and making sure that everybody works together. So that can be one of the functions of the MWS. So that was for preparation stage. Now, looking at the operation execution and the storyboard part. So the first thing, obviously, the first thing, obviously, is to bring the heavy lift vessel and make sure that the radius that was defined to operate is set as the target, and that the vessel can maintain its position. The vessel is here on DP mode, for example, but you could have bow mooring lines, for example, or anchors that are being used. If you want to be able, for example, to manage a DP failure, making sure that you're not going to hit the foundation, it's a case where you could have bow mooring lines installed with drag anchors, for example, where you maintain a minimum tension on them. And if you lose propulsion or DP capability, you can use your mooring winch to gain space. You aboard your operation and your lifting operation, and you gain clearance between the two. So it is also a matter of making sure that the position of the asset is not going to be above mooring lines. And usually you would try not to work above your cable export corridor when you can. So you would favor to be away from it. For example, if the cables are here, you will try to shift a bit. The idea is only that in case of drop object, in terms of an anchor ripping, you don't want this to damage your cable. So it's taking into consideration what's happening at the surface, but also what's happening under. So once you've defined the right position, the first activity that you will have to do is to remove the TP cover. So in your case, you don't really have a TP that is being defined, but basically, on top of your main column, you will have either just a mechanical interface, a flange, and you remove, and you just have a cover to protect that was protecting this flange. But today, in the practice in bottom fixed has been to have transition piece that includes your electrical equipment, your switch gear, your basically what's going to make the connection between your inter-array cables and the turbine itself. Usually, today, the practice is to locate it within the TP, within the transition piece. There are cases now where monopiles are being installed without transition piece, and where these equipments are being located in the bottom section of the tower. But it's basically to allow for hammering of monopiles, like bigger monopiles that need hammering, because you cannot hammer on top of a TP. If you hammer on top of the TP, your electrical equipment they're gone. So it's you remove an interface, you remove a flange. It allows more efficient piling or piling after drilling, and then you install your bottom your tower directly with the electrical equipment. So today, in your case, it's either you're going to have some equipment maybe at the top of your main column, or you will have an interface structure. But yeah, the idea is you will have a protection always on this, either to protect your electrical equipment or to protect the structure, and you need to remove it. That's the first thing to do. So then once you have the, let's say, you're in the preparation stage, you can already prepare the rigging and prepare, here it's already shown being lifted, but basically you can prepare your rigging, you can prepare everything for your bottom section. You need to finalize, so usually you would have left the port with it, but what we saw before, which is your installation guides, any temporary, as we said, tethering device, anything that you will use on the foundation to guide and bring the column in position, you need to have everything ready. Then you get your go-ahead in terms of weather. So anything that happens before, basically, you can stop the operation anytime. There is no problem. But once you give your go-ahead and you open your operation window, then usually you would close the gap with the foundation to be at your defined radius. So all these preparation steps, you can do them a bit further. You remove the sea fastening of the tower component, in this case, the tower component. So usually these sea fastenings, now they are mostly mechanical. It's not welded, it's bolted, or it's using bracing and power system. So you remove the sea fastening, you lift your column, get it into position on your interface structure. And once you have secured and you've started basically bolting the bottom section, remove your rigging on top. Then your first activity is actually to gain access to install the installation aids for the next section. And that's actually going to be the activity that is going to be a bit critical in terms of time is how much of this installation aids do you want to pre-install on the column here, for example, before lifting, or do you install it after? So again, it's a matter of philosophy. You can try to pre-install as much as you want before, but it comes with the risk that first your part goes heavier, and you increase the risk of clash with your rigging system. Then once you have the guiding section that is ready, and you have done all your guide installation on top of the bottom section, then you're ready for the next one. I will not go in the detail of everyone, but basically this is a repeat of the same thing about waiting for the right weather window, lifting the section, providing access, and preparing for the next stage. So every step, basically, you're repeating the same thing. Your target radius usually will not change. Your vessel will stay at the same position. But every time that you're doing operations that are not the direct lift operation, so anything that is about preparation before the go-ahead, you can gain clearance between the two. You can basically back off from the foundation to maintain your clearance. And only when you have your weather operation opening for the lift, then you get into the effective lifting position. So same goes for all your turbine column sections until you get to the RNA. And that's actually the most critical lift. It is your heaviest component at the highest height. So that's what we're saying. In this case, this is the green jade crane. You can see that the distance, I mean, you had a lot of spare, if I show the previous one. You had a lot of spare hook heights between your top, the top of your column and your limits. When you're looking at the RNA, you have to operate at a very small radius to a point where the clearance between the RNA and the boom here is extremely small. I forgot how much it is on the drawing, but basically it's not much. And it is your heaviest and highest lift. So if there was one lift to look at to size your operation, actually you would only look at this one, because that's the one that's going to be the most stringent in terms of hook height and weight. And as I said, until now, the OEM interface between the RNA and the top part of the column is the one where the OEM, let's say, are the most stringent to guide. To guide a column to a column with flange, they don't have much to say. You know, I mean, it's two metal cylinders with two flanges. It's easy. Here, what you need to understand is that this is packed with mechanical, electrical equipment, with all this, and they have very little clearances today between the flange, which is inside the bottom of the RNA, and the tower. So then, once this lift is passed, you gain a little bit of clearance, but it's more that the blades are a lot lighter also. The blades have a different set of constraints when being lifted, which is that because they are good at catching wind, their relative motion are always greater than the rest. They have a windage area that's bigger, and that's why you see specialized motion compensated grippers for the blades on bottom fix today. You don't see that for the nacelle or for the column. They are still lifting with normal spreader bars. Because the lift, even for floating to fix, is critical and is very sensitive to motion. Now, because there are components that are much lighter, around 60 tons, they are fairly easy to guide and to bring in the RNA. If you've seen some video, basically they are nearly guiding it. They just use tether lines to bring the blade in, and they have guiding pins, like long guiding pins, that help center and position the position directly from the plane. And then it's very similar to what you would do on bottom fix. You do rotations of the hub to provide access to basically to always have an horizontal lift for your blade, and always be with the same approach to your RNA. Obviously, the orientation of your rotor here has to be made in conjunction with the prevailing weather that you have at the time. You won't relocate and reposition your asset every time you lift the blade, but you need to make sure that the direction that you give. So once you have your RNA in, basically, you can control the position of your RNA with regards to your foundation. So it's one important point is to look at what orientation do you want to give to minimize the motions when you do the blade integration. And obviously, the last step is demobilizing the heavy lift vessel once all your blades are installed. Then, I mean, it's not part of the presentation, but obviously you have offshore commissioning. I mean, you have mechanical completion activities that have to be done on the turbine. You have offshore commissioning of activities that have to be done on the turbine, but there are no difference from what you would have done at quayside or on bottom fixed foundation. So that's fairly, I would say, straightforward. It's something that there is already a return of experience on. So that was the smallest of the three parts. More or less on time. Do you have questions or any things that you would like to discuss a bit more about? A lot of unknowns, I know, on this section, but very interesting. Lots of research group. There are a few GIPs on the topic.
以前就是那个压载，就是它是一边吊一边打的嘛，还是每个阶段是先打空一部分的水，还是这样？
So the ballast system is when we lifting the power on the sail.
Yeah.
It's a ballast system is the motion at the same time, working at the same time or not?
No. You will have a static ballast configuration. You have two options. Either you have one configuration of ballast at the start, where you remove ballast on your main column. And as you increase the weight, basically you will gain the even keel by adding the weight of your column. And your COG will basically go to the final position. That can work if your foundation can take a configuration with a bit of list, with a ballast that's basically not symmetrical with your main column. You can do that. It's like this. You don't have to touch your ballast during the operation. The other possibility is you start even keel, you lift your components, then you adjust your ballast to get back to even keel. Lift your next component, adjust again, lift, adjust again, lift, adjust again. This ballasting operation, because of the weight you're adding is very small. We're talking about a few hundred tons. So it's just 100 cubic meters of water to transfer. So it's fairly fast, and that's not weather sensitive. You can do it as you're preparing your installation aids. You can reconfigure your ballast. So it's not time on the schedule. It's not time critical. A bit more work, but yeah, it's both possibility can do. Yeah. Guys, don't worry. This afternoon, the session on load out and float off, there is a lot more to say. I mean, there is a lot more experience to it also. But basically, what's interesting on this part is really to show that today it is something that is not much. It's not mature at all. It's not mature on the assets that can help us. It's not mature on the OEM side. And today, because of the bottom fix race in getting bigger turbines and also going deeper in the sea, I mean, we said 60 meters today. Bottom fix is doing. It means that floating today, because the market size being so much smaller, to see assets specialized in floating or to cope with this kind of problem, it's not going to happen very soon. So it's going to be relying a lot on the engineering and a lot on finding smart ways to use assets that are existing in the bottom fix to make it work. And that might mean, as I said, very creative guiding techniques, coupling the units. I mean, even on the wider, the more crazy thought, in theory, you could try to couple physically using, like, for example, a spacer bar, the lifting vessel and the foundation, to try to moor them together and lift the turbine components with this block of units. That means that the foundation needs to be able to take the pressure from the spacer barge coming from the vessel. But maybe that's going to be where we end up, meaning having to control so much the motion that we need to make a system that's a lot more stiff to get closer to the fixed to floating or floating to fixed condition that we have already experienced. But yeah, it's an interesting one. I encourage you to watch. I mean, I haven't put it here, but just watch an offshore lift of like a topside on a barge or not on a jacket, on another floating foundation, like a mating, for example, of a floating structure via a lift offshore. They have a lot of, for example, units to absorb the shocks, to absorb the dynamics, to couple the motions of the two. So like the LMU units, for example, that they use at the bottom of topsides. It's really about providing an elastic connection between the two structures. And this elastic structure, basically the response of it will align the response. One of the structure will impose its own motion response to the other one through this elastic connection. So that once you get a coupled, like a synchronous movement of the two, then they can land. But when you watch the videos, they can wait, I don't know, 20 minutes, 30 minutes to get a proper series of waves, wind, anything that will make the system to be aligned so that they can land. But they will stay, let's say, at the heave variations, depending on how much they have, maybe 40, 50 centimeters away from their target for 20, 30 minutes until they can couple the LNUs, until they can land. So, and that's, we are talking about modules that can be 5,000, 7,000 tons on a transportation barge, for example, or something like this. Here we're talking about two floating bodies. It's lighter, but it's also more sensitive to wind, more sensitive to this kind of factor. It's less stiff. The lifting arrangements for these very heavy topsides are very stiff. You have multiple spreader bars. Usually they are controlled by multiple hooks on the cranes. When here, single hook lifts, basically you have control of rotations to do. You have a lot more degree of freedom for your cargo to move. It's strange. Okay. Well, if we are good, then we can break there. And I think we start at 2, I think. Yeah.
2. Okay.
If that's okay with you, or earlier if you want, but
okay. Okay, so
okay.
Let's take a break. Come back at 2. Yeah. Thank you.
Okay, thank you.